I'm sure you all agree that machine learning is one of the hottest trends in today's market, right? Gartner predicts that by 2022, there will be at least 40% of new application development projects going on in the market that would be requiring machine learning co-developers on their team. It's expected that these projects would generate a revenue of around $3.9 trillion. Isn't it huge? So looking at the huge upcoming demand of machine learning around the world, we guys at Edureka have come up and designed a well-structured machine learning full course for you guys. But before we actually drill down over there, let me just introduce myself. Hello all, I'm Atul from Edureka and today I'll be guiding you through this entire machine learning course. Well, this course has been designed in a way that you get the most out of it. So we'll slowly and gradually start with the beginner level and then move towards the advanced topic. So without delaying any further, let's start with the agenda of today's session. Our machine learning course has been segregated into 6 different modules. We'll start our first module with Introduction to Machine Learning. Here we'll discuss things like what exactly is machine learning, how it differs from artificial intelligence and deep learning, what are its various types, what are its various applications, and finally we'll end our first module with a basic demo in Python. Okay? Our second module focuses on stats and probability. Here we'll cover things like descriptive statistics, inferential statistics, probability theory, and so on. Our third module is on supervised learning. Well, supervised learning is one of a type of machine learning which focuses mainly on regression and classification type of problem. It deals with labeled datasets and the algorithm which are a part of it are linear regression, logistic regression, naive Bayes, random forest, decision tree, and so on. Our fourth module is on unsupervised learning. Well, this module focuses mainly on dealing with unlabeled datasets and the algorithm which are a part of it are k-means algorithm and a priori algorithm. As a part of fifth module, we have reinforcement learning. Here we are going to discuss about reinforcement learning in depth and also about Q-learning algorithm. Finally, in the end, it's all about to make you industry ready. Okay, so here we are going to discuss about 3 different projects which are based on supervised learning, unsupervised learning, and reinforcement learning. Finally, in the end, I'll tell you about some of the skills that you need to become a machine learning engineer. Okay, and also I'll be discussing about some of the important questions that are asked in a machine learning interview. Fine. With this, we come to the end of this agenda. Before you move ahead, don't forget to subscribe to Edureka and press the bell icon to never miss any update from us.
Hello everyone, this is Atul from Edureka and welcome to today's session on what is machine learning. As you know, we are living in a world of humans and machines. The humans have been evolving and learning from the past experience since millions of years. On the other hand, the era of machines and robots have just begun. In today's world, these machines or the robots are like they need to be programmed before they actually follow your instructions. But what if the machines started to learn on their own? And this is where machine learning comes into picture. Machine learning is the core of many futuristic technological advancement in our world. Today you can see various examples or implementation of machine learning around us, such as Tesla's self-driving car, Apple Siri, Sophia AI robot, and many more are there. So what exactly is machine learning? Well, machine learning is a subfield of artificial intelligence that focuses on the design of system that can learn from and make decisions and predictions based on the experience, which is data in the case of machines. Machine learning enables computer to act and make data-driven decisions rather than being explicitly programmed to carry out a certain task. These programs are designed to learn and improve over time when exposed to new data. Let's move on and discuss one of the biggest confusion of the people in the world. They think that all the 3 of them, the AI, the machine learning, and the deep learning, all are same. You know what? They are wrong. Let me clarify things for you. Artificial intelligence is a broader concept of machines being able to carry out tasks in a smarter way. It covers anything which enables the computer to behave like humans. Think of a famous Turing test to determine whether a computer is capable of thinking like a human being or not. If you're talking to Siri on your phone and you get an answer, you're already very close to it. So this was about the artificial intelligence. Now coming to the machine learning part. So as I already said, machine learning is a subset or a current application of AI. It is based on the idea that we should be able to give machine the access to data and let them learn from themselves. It's a subset of artificial intelligence that deals with the extraction of pattern from dataset. This means that the machine can not only find the rules for optimal behavior, but also can adapt to the changes in the world. Many of the algorithms involved have been known for decades, centuries even. Thanks to the advances in the computer science and parallel computing, they can now scale up to massive data volumes. So this was about the machine learning part. Now coming over to deep learning. Deep learning is a subset of machine learning where similar machine learning algorithms are used to train deep neural networks so as to achieve better accuracy in those cases where former was not performing up to the mark. Right. I hope now you understood that machine learning, AI, and deep learning, all three are different. Okay, moving on ahead. Let's see, in general, how a machine learning works. One of the approaches is where the machine learning algorithm is trained using a labeled or unlabeled training dataset to produce a model. New input data is introduced to the machine learning algorithm and it makes prediction based on the model. The prediction is evaluated for accuracy, and if the accuracy is acceptable, the machine learning algorithm is deployed. Now, if the accuracy is not acceptable, the machine learning algorithm is trained again and again with an augmented training dataset. This was just a high-level example, as there are many more factors and other steps involved in it. Now let's move on and subcategorize the machine learning into three different types: the supervised learning, unsupervised learning, and reinforcement learning. And let's see what each of them are, how they work, and how each of them is used in the field of banking, healthcare, retail, and other domains. Don't worry, I'll make sure that I use enough examples and implementation of all three of them to give you a proper understanding of it. So starting with supervised learning. What is it? So let's see a mathematical definition of supervised learning. Supervised learning is where you have input variables x and an output variable y, and you use an algorithm to learn the mapping function from the input to the output, that is y equal fx. The goal is to approximate the mapping function so well that whenever you have a new input data x, you could predict the output variable, that is y, for that data. Right. I think this was confusing for you. Let me simplify the definition of supervised learning. So we can rephrase the understanding of the mathematical definition as a machine learning method where each instances of a training dataset is composed of different input attribute and an expected output. The input attributes of a training dataset can be of any kind of data. It can be a pixel of image, it can be a value of a database row, or it can even be an audio frequency histogram, right? For each input instance, an expected output value is associated. The value can be discrete, representing a category, or can be a real or continuous value. In either case, the algorithm learns the input pattern that generates the expected output. Now, once the algorithm is trained, it can be used to predict the correct output of a never seen input. You can see an image on your screen, right? In this image, you can see that we are feeding raw inputs as image of apple to the algorithm. As a part of the algorithm, we have a supervisor who keeps on correcting the machine or who keeps on training the machine. It keeps on telling him that yes, it is an apple, and no, it is not an apple. Things like that. So this process keeps on repeating until we get a final trained model. Once the model is ready, it can easily predict the correct output of a never seen input. In this slide, you can see that we are giving an image of a green apple to the machine, and the machine can easily identify it as yes, it is an apple and it is giving the correct result, right? Let me make things more clearer to you. Let's discuss another example of it. So in this slide, the image shows an example of a supervised learning process used to produce a model which is capable of recognizing the ducks in the image. The training dataset is composed of labeled picture of ducks and non-ducks. The result of supervised learning process is a predictive model which is capable of associating a label duck or not duck to the new image presented to the model. Now, once trained, the resulting predictive model can be deployed to the production environment. You can say a mobile app, for example. Once deployed, it is ready to recognize the new pictures. Right. Now you might be wondering why this category of machine learning is named as supervised learning. Well, it is called as supervised learning because the process of an algorithm learning from the training dataset can be thought of as a teacher supervising the learning process. We know the correct answers. The algorithm iteratively makes while predicting on the training data and is corrected by the teacher. The learning stops when the algorithm achieves an acceptable level of performance. Now let's move on and see some of the popular supervised learning algorithms. So we have linear regression, random forest, and support vector machines. These are just for your information. We'll discuss about these algorithms in our next video. Now let's see some of the popular use cases of supervised learning. So we have Cortana. Cortana or any other speech automation in your mobile phone trains using your voice. And once trained, it start working based on that training. This is an application of supervised learning. Suppose you are telling, okay, Google, call Sam, or you say, hey Siri, call Sam. You get an answer to it, and the action is performed, and automatically a call goes to Sam. So these are just an example of supervised learning. Next comes the weather app. Based on some of the prior knowledge, like when it is sunny, the temperature is higher. When it is cloudy, humidity is higher. Any kind of that, they predict the parameters for a given time. So this is also an example of supervised learning, as we are feeding the data to the machine and telling that whenever it is sunny, the temperature should be higher. Whenever it is cloudy, the humidity should be higher. So it's an example of supervised learning. Another example is biometric attendance, where you train the machine and after a couple of inputs of your biometric identity, be it your thumb, your iris, or your earlobe, or anything, once trained, the machine can validate your future input and can identify you. Next comes in the field of banking sector. In banking sector, supervised learning is used to predict the credit worthiness of a credit card holder by building a machine learning model to look for faulty attributes by providing it with a data on delinquent and non-delinquent customers. Next comes the healthcare sector. In the healthcare sector, it is used to predict the patient's readmission rates by building a regression model by providing data on the patient's treatment administration and readmissions to show variables that best correlate with readmission. Next comes the retail sector. In retail sector, it is used to analyze the product that a customer buy together. It does this by building a supervised model to identify frequent item sets and association rule from the transactional data. Now let's learn about the next category of machine learning, the unsupervised part. Mathematically, unsupervised learning is where you only have input data X and no corresponding output variable. The goal for unsupervised learning is to model the underlying structure or distribution in the data in order to learn more about the data. So let me rephrase you this in simple terms. In unsupervised learning approach, the data instances of a training dataset do not have an expected output associated to them. Instead, unsupervised learning algorithm detects pattern based on innate characteristics of the input data. An example of machine learning task that applies unsupervised learning is clustering. In this task, similar data instances are grouped together in order to identify clusters of data. In this slide, you can see that initially we have different varieties of fruits as input. Now these set of fruits as input X are given to the model. Now once the model is trained using unsupervised learning algorithm, the model will create clusters on the basis of its training. It will group the similar fruits and make their cluster. Let me make things more clearer to you. Let's take another example of it. So in this slide, the image below shows an example of unsupervised learning process. This algorithm processes an unlabeled training dataset, and based on the characteristics, it groups the picture into 3 different clusters of data. Despite the ability of grouping similar data into clusters, the algorithm is not capable to add labels to the group. The algorithm only knows which data instances are similar, but it cannot identify the meaning of this group. So now you might be wondering why this category of machine learning is named as unsupervised learning. So these are called as unsupervised learning because unlike supervised learning, above there are no correct answers and there is no teacher. Algorithms are left on their own to discover and present the interesting structure in the data. Let's move on and see some of the popular unsupervised learning algorithm. So we have here k-means, a priori algorithm, and hierarchical clustering. Now let's move on and see some of the examples of unsupervised learning. Suppose a friend invites you to his party and where you meet totally strangers. Now you'll classify them using unsupervised learning as you don't have any prior knowledge about them. And this classification can be done on the basis of gender, age group, dressing, educational qualification, or whatever way you might like. Now why this learning is different from supervised learning? Since you didn't use any past or prior knowledge about the people, you kept on classifying them on the go. As they kept on coming, you kept on classifying them. Yeah, this category of people belong to this group, this category of people belong to that group, and so on. Okay, let's see one more example. Let's suppose you have never seen a football match before, and by chance you watch a video on the internet. Now you can easily classify the players on the basis of different criterion, like player wearing the same kind of jersey are in one class, player wearing different kind of jersey are in different class. Or you can classify them on the basis of their playing style, like the guy is an attacker, so he's in one class. He's a defender, he's in another class. Or you can classify them whatever way you observe the things. So this was also an example of unsupervised learning. Let's move on and see how unsupervised learning is used in the sectors of banking, healthcare, and retail. So starting with banking sector. So in banking sector, it is used to segment customers by behavioral characteristic by surveying prospects and customers to develop multiple segments using clustering. In healthcare sector, it is used to categorize the MRI data by normal or abnormal images. It uses deep learning techniques to build a model that learns from different features of images to recognize a different pattern. Next is the retail sector. In retail sector, it is used to recommend the products to customer based on their past purchases. It does this by building a collaborative filtering model based on the past purchases by them. I assume you guys now have a proper idea of what unsupervised learning means. If you have any slightest doubt, don't hesitate and add your doubt to the comment section. So let's discuss the third and the last type of machine learning, that is reinforcement learning. So what is reinforcement learning? Well, reinforcement learning is a type of machine learning algorithm which allows software agents and machine to automatically determine the ideal behavior within a specific context to maximize its performance. The reinforcement learning is about interaction between two elements, the environment and the learning agent. The learning agent leverages two mechanisms, namely exploration and exploitation. When learning agent acts on trial and error basis, it is termed as exploration. And when it acts based on the knowledge gained from the environment, it is referred to as exploitation. Now, this environment rewards the agent for correct actions, which is reinforcement signal. Leveraging the rewards obtained, the agent improves its environment knowledge to select the next action. In this image, you can see that the machine is confused whether it is an apple or it's not an apple. Then the machine is trained using reinforcement learning. If it makes correct decision, it gets rewards point for it. And in case of wrong, it gets a penalty for that. Once the training is done, now the machine can easily identify which one of them is an apple. Let's see an example. Here we can see that we have an agent who has to judge from the environment to find out which of the two is a duck. The first task he did is to observe the environment. Next, he selects some action using some policy. It seems that the machine has made a wrong decision by choosing a bunny as a duck. So the machine will get penalty for it. For example, minus 50 point for a wrong answer. Right. Now the machine will update its policy and this will continue till the machine gets an optimal policy. From the next time, machine will know that bunny is not a duck. Let's see some of the use cases of reinforcement learning. But before that, let's see how Pavlov trained his dog using reinforcement learning, or how he applied the reinforcement method to train his dog. Pavlov integrated learning in 4 stages. Initially, Pavlov gave meat to his dog, and in response to the meat, the dog started salivating. Next, what he did, he created a sound with the bell. For this, the dog did not respond anything. In the third part, he tried to condition the dog by using the bell and then giving him the food. Seeing the food, the dog started salivating. Eventually, a situation came when the dog started salivating just after hearing the bell, even if the food was not given to him, as the dog was reinforced that whenever the master will ring the bell, he will get the food. Now let's move on and see how reinforcement learning is applied in the field of banking, healthcare, and retail sector. So starting with the banking sector. In banking sector, reinforcement learning is used to create a next best offer model for a call center by building a predictive model that learns over time as user accept or reject offer made by the sales staff. Fine. Now in healthcare sector, it is used to allocate the scarce medical resources to handle different type of ER cases by building a Markov decision process that learns treatment strategies for each type of ER case. Next and the last comes the retail sector. So let's see how reinforcement learning is applied to retail sector. In retail sector, it can be used to reduce excess stock with dynamic pricing by building a dynamic pricing model that adjusts the price based on customer response to the offers. I hope by now you have attained some understanding of what is machine learning and you are ready to move ahead. Welcome to today's topic of discussion on AI versus machine learning versus deep learning. These are the terms which have confused a lot of people, and if you two are one among them, let me resolve it for you. Well, artificial intelligence is a broader umbrella under which machine learning and deep learning come. You can also see in the diagram that even deep learning is a subset of machine learning. So you can say that all three of them, the AI, the machine learning, and deep learning, are just the subset of each other. So let's move on and understand how exactly they differ from each other. So let's start with artificial intelligence. The term artificial intelligence was first coined in the year 1956. The concept is pretty old, but it has gained its popularity recently. But why? Well, the reason is earlier we had very small amount of data. The data we had was not enough to predict the accurate result. But now there's a tremendous increase in the amount of data. Statistics suggest that by 2020, the accumulated volume of data will increase from 4.4 zettabytes to roughly around 44 zettabytes or 44 trillion GBs of data. Along with such enormous amount of data, now we have more advanced algorithm and high-end computing power and storage that can deal with such large amount of data. As a result, it is expected that 70% of enterprise will implement AI over the next 12 months, which is up from 40% in 2016 and 51% in 2017. Just for your understanding, what is AI? Well, it's nothing but a technique that enables the machine to act like humans by replicating the behavior and nature. With AI, it is possible for a machine to learn from the experience. The machines adjust their responses based on new input, thereby performing human-like tasks. Artificial intelligence can be trained to accomplish specific tasks by processing large amount of data and recognizing pattern in them. You can consider that building an artificial intelligence is like building a church. The first church took generations to finish, so most of the workers who were working in it never saw the final outcome. Those working on it took pride in their crafts, building bricks and chiseling stone that was going to be placed into the great structure. So as AI researchers, we should think of ourselves as humble brick makers whose job is to study how to build components, example parsers, planners, or learning algorithm, or etc. anything that someday someone and somewhere will integrate into the intelligent systems. Some of the examples of artificial intelligence from our day-to-day life are Apple Series, chess playing computer, Tesla's self-driving car, and many more. These examples are based on deep learning and natural language processing. Well, this was about what is AI and how it gains its hype. So moving on ahead, let's discuss about machine learning and see what it is and why it was even introduced. Well, machine learning came into existence in the late 80s and the early 90s. But what were the issues with the people which made the machine learning come into existence? Let us discuss them one by one. In the field of statistics, the problem was how to efficiently train large complex model. In the field of computer science and artificial intelligence, the problem was how to train more robust version of AI system. While in the case of neuroscience, problem faced by the researchers was how to design operational model of the brain. So these were some of the issues which had the largest influence and led to the existence of the machine learning. Now this machine learning shifted its focus from the symbolic approaches it had inherited from the AI and moved towards the methods and model it had borrowed from statistics and probability theory. So let's proceed and see what exactly is machine learning. Well, machine learning is a subset of AI which enables the computer to act and make data-driven decisions to carry out a certain task. These programs or algorithms are designed in a way that they can learn and improve over time when exposed to new data. Let's see an example of machine learning. Let's say you want to create a system which tells the expected weight of a person based on its height. The first thing you do is you collect the data. Let's see, this is how your data looks like. Now each point on the graph represents one data point. To start with, we can draw a simple line to predict the weight based on the height. For example, a simple line W equal H minus 100, where W is weight in kgs and H is height in centimeter. This line can help us to make the prediction. Our main goal is to reduce the difference between the estimated value and the actual value. So in order to achieve it, we try to draw a straight line that fits through all these different points and minimize the error. So our main goal is to minimize the error and make them as small as possible. Decreasing the error or the difference between the actual value and estimated value increases the performance of the model. Further on, the more data points we collect, the better our model will become. We can also improve our model by adding more variables and creating different prediction lines for them. Once the line is created, so from the next time if we feed a new data, for example height of a person to the model, it would easily predict the data for you and it will tell you what his predicted weight could be. I hope you got a clear understanding of machine learning. So moving on ahead, let's learn about deep learning. Now what is deep learning? You can consider deep learning model as a rocket engine, and its fuel is its huge amount of data that we feed to these algorithms. The concept of deep learning is not new, but recently its hype has increased and deep learning is getting more attention. This field is a particular kind of machine learning that is inspired by the functionality of our brain cells called neuron, which led to the concept of artificial neural network. It simply takes the data connection between all the artificial neurons and adjusts them according to the data pattern. More neurons are added if the size of the data is large. It automatically features learning at multiple levels of abstraction, thereby allowing a system to learn complex function mapping without depending on any specific algorithm. You know what? No one actually knows what happens inside a neural network and why it works so well. So currently you can call it as a black box. Let us discuss some of the example of deep learning and understand it in a better way. Let me start with a simple example and explain you how things happen at a conceptual level. Let us try and understand how you recognize a square from other shapes. The first thing you do is you check whether there are four lines associated with the figure or not. Simple concept, right? If yes, we further check if they are connected and closed. Again, if yes, we finally check whether it is perpendicular and all its sides are equal. Correct? If everything fulfills, yes, it is a square. Well, it is nothing but a nested hierarchy of concepts. What we did here, we took a complex task of identifying a square in this case and broke it into simpler tasks. Now this deep learning also does the same thing but at a larger scale. Let's take an example of machine which recognizes the animal. The task of the machine is to recognize whether the given image is of a cat or of a dog. What if we were asked to resolve the same issue using the concept of machine learning? What we would do? First, we would define the features such as check whether the animal has whiskers or not, or check if the animal has pointed ears or not, or whether its tail is straight or curved. In short, we will define the facial features and let the system identify which features are more important in classifying a particular animal. Now, when it comes to deep learning, it takes this to one step ahead. Deep learning automatically finds out the feature which are most important for classification, compared to machine learning, where we had to manually give out that features. By now, I guess you have understood that AI is the bigger picture and machine learning and deep learning are its subpart. So let's move on and focus our discussion on machine learning and deep learning. The easiest way to understand the difference between the machine learning and deep learning is to know that deep learning is machine learning. More specifically, it is the next evolution of machine learning. Let's take few important parameters and compare machine learning with deep learning. So starting with data dependencies. The most important difference between deep learning and machine learning is its performance as the volume of the data gets increased. From the below graph, you can see that when the size of the data is small, deep learning algorithm doesn't perform that well. But why? Well, this is because deep learning algorithm needs a large amount of data to understand it perfectly. On the other hand, the machine learning algorithm can easily work with smaller data set. Fine. Next comes the hardware dependencies. Deep learning algorithms are heavily dependent on high-end machines, while the machine learning algorithm can work on low-end machines as well. This is because the requirement of deep learning algorithm include GPUs, which is an integral part of its working. The deep learning algorithm requires GPUs as they do a large amount of matrix multiplication operations, and these operations can only be efficiently optimized using a GPU as it is built for this purpose only. Our third parameter will be feature engineering. Well, feature engineering is a process of putting the domain knowledge to reduce the complexity of the data and make patterns more visible to learning algorithms. This process is difficult and expensive in terms of time and expertise. In case of machine learning, most of the features are needed to be identified by an expert and then hand-coded as per the domain and the data type. For example, the features can be a pixel value, shapes, texture, position, orientation, or anything. Fine. The performance of most of the machine learning algorithm depends on how accurately the features are identified and extracted. Whereas in case of deep learning algorithms, it tries to learn high-level features from the data. This is a very distinctive part of deep learning, which makes it way ahead of traditional machine learning. Deep learning reduces the task of developing new feature extractor for every problem. Like in the case of CNN algorithm, it first tries to learn the low-level features of the image, such as edges and lines, and then it proceeds to the parts of faces of people, and then finally to the high-level representation of the face. I hope the things are getting clear to you. So let's move on ahead and see the next parameter. So our next parameter is problem solving approach. When we are solving a problem using traditional machine learning algorithm, it is generally recommended that we first break down the problem into different subparts, solve them individually, and then finally combine them to get the desired result. So this is how the machine learning algorithm handles the problem. On the other hand, the deep learning algorithm solves the problem from end to end. Let's take an example to understand this. Suppose you have a task of multiple object detection, and your task is to identify what is the object and where it is present in the image. So let's see and compare how will you tackle this issue using the concept of machine learning and deep learning. Starting with machine learning, in a typical machine learning approach, you would first divide the problem into two steps. First, object detection and then object recognition. First of all, you would use a bounding box detection algorithm like GrabCut, for example, to scan through the image and find out all the possible objects. Now, once the objects are recognized, you would use object recognition algorithm like SVM with HOG to recognize relevant objects. Now, finally, when you combine the result, you would be able to identify what is the object and where it is present in the image. On the other hand, in deep learning approach, you would do the process from end to end. For example, in a YOLONet, which is a type of deep learning algorithm, you would pass an image and it would give out the location along with the name of the object. Now let's move on to our fifth comparison parameter. It's execution time. Usually, a deep learning algorithm takes a long time to train. This is because there are so many parameters in a deep learning algorithm that makes the training longer than usual. The training might even last for 2 weeks or more than that if you're training completely from the scratch. Whereas in the case of machine learning, it relatively takes much less time to train, ranging from a few weeks to few hours. Now the execution time is completely reversed when it comes to the testing of data. During testing, the deep learning algorithm takes much less time to run. Whereas if you compare it with the KNN algorithm, which is a type of machine learning algorithm, the test time increases as the size of the data increase. Last but not the least, we have interpretability as a factor for comparison of machine learning and deep learning. This factor is the main reason why deep learning is still thought 10 times before anyone uses it in the industry. Let's take an example. Suppose we use deep learning to give automated scoring to essays. The performance it gives in scoring is quite excellent and is near to the human performance. But there's an issue with it. It does not reveal why it has given that score. Indeed, mathematically it is possible to find out that which node of a deep neural network were activated, but we don't know what the neurons were supposed to model and what these layers of neuron were doing collectively. So we fail to interpret the result. On the other hand, machine learning algorithm like decision tree gives us a crisp rule for why it chose and what it chose. So it is particularly easy to interpret the reasoning behind it. Therefore, the algorithms like decision tree and linear or logistic regression are primarily used in industry for interpretability. Let me summarize things for you. Machine learning uses algorithm to parse the data, learn from the data, and make informed decision based on what it has learned. Fine. Now this deep learning structures algorithms in layers to create artificial neural network that can learn and make intelligent decisions on their own. Finally, deep learning is a subfield of machine learning, while both fall under the broad category of artificial intelligence. Deep learning is usually what's behind the most human-like artificial intelligence.
Now, in early days, scientists used to have a lab notebook to record tests, progress, results, and conclusions. Now, Jupyter is a modern-day tool that allows data scientists to record their complete analysis process, much in the same way other scientists use a lab notebook. Now, the Jupyter product was originally developed as a part of IPython project. The IPython project was used to provide interactive online access to Python. Over time, it became useful to interact with other data analysis tools such as R in the same manner. With the split from Python, the tool grew into its current manifestation of Jupyter. Now, IPython is still an active tool that's available for use. The name Jupyter itself is derived from the combination of Julia, Python, and R. While Jupyter runs code in many programming languages, Python is a requirement for installing the Jupyter Notebook itself. Now, to download Jupyter Notebook, there are a few ways. In their official website, it is strongly recommended installing Python and Jupyter using Anaconda distribution. which includes Python, the Jupyter Notebook, and other commonly used packages for scientific computing as well as data science. Although one can also do so using the pip installation method. Personally, what I would suggest is downloading Anaconda Navigator, which is a desktop graphical user interface included in Anaconda. Now, this allows you to launch application and easily manage Conda packages, environments, and channels without the need to use command line commands. So all you need to do is go to anaconda.org, and inside you go to Anaconda Navigator. So as you can see here, we have the Conda installation code, which you're going to use to install it in your particular PC. So either you can use these installers. So once you download the Anaconda Navigator, it looks something like this. So as you can see here, we have Jupyter Lab, Jupyter Notebook, we have Qt Console, which is an IPython console. We have Spider, which is somewhat similar to RStudio in terms of Python. Again, we have RStudio also, we have Orange 3, we have GlueViz, and we have VSC Code. Our focus today would be on this Jupyter Notebook itself. Now, when you launch the Navigator, you can see there are many options available for launching Python as well as R instances. Now, by definition, a Jupyter Notebook is fundamentally a JSON file with a number of annotations. Now, it has three main parts, which are the metadata, the notebook format, and the list of cells. Now, you should get yourself acquainted with the environment. The Jupyter user interface has a number of components. So it's important to know what are components you should be using on a daily basis, and you should get acquainted with it. So as you can see here, our focus today will be on the Jupyter Notebook. So let me just launch the Jupyter Notebook. Now what it does is creates an online Python instance for you to use it over the web. So let it launch. Now as you can see, we have Jupyter on the top left as expected. And this acts as a button to go to your home page. Whenever you click on this, you get back to your particular home page, that is the dashboard. Now there are three tabs displayed, which are the files, running, and clusters. And what we'll do is we'll understand all of these three and understand what are the importance of these three tabs. The file tab shows the list of the current files in the directory. So as you can see, we have so many files here. Now the running tab presents another screen of the currently running processes and the notebooks. Now the drop-down list for the terminals and notebooks are populated with their running numbers. So as you can see inside, we do not have any running terminals or there are no running notebooks as of now. And the cluster tab presents another screen to display the list of clusters available. So in the top right corner of the screen, there are three buttons, which are upload, new, and the refresh button. Let me go back here. So as you can see here, we have the upload, new, and the refresh button. Now the upload button is used to add files to the notebook space, and you may also just drag and drop as you would when handling files. Similarly, you can drag and drop notebooks into specific folders as well. Now the menu with the new in the top presents a further menu of text file, folders, terminal, and Python 3. Now the text file option is used to add a text file to the current directory. Now Jupyter will open a new browser window for you for the running new text editor. Now the text entered is automatically saved and will be displayed in your notebook's files display. Now the folder option, what it does is creates a new folder with the name untitled folder, and remember, all the files and folder names are editable. Now the terminal option allows you to start an IPython session. The notebook options available will be activated when additional notebooks are available in your environment. The Python 3 option is used to begin Python 3 session interactively in your notebook. The interface looks like the following screenshot. Now what you have is full file editing capabilities for your script, including saving as new file. You also have a complete working ID for your Python script. Now if we come to the refresh button, the refresh button is used to update the display. It's not really necessary as the display is reactive to any changes in the underlying file structure. And at the top of the Files tab item, there is a checkbox, a drop-down menu, and a home button. As you can see here, we have the checkbox, the drop-down menu, and the home button. Now the checkbox is used to toggle all the checkboxes in the item list. So as you can see, you can select all of these. You can either move or either delete all of the files selected. Or what you can do is select all and deselect some of the files. That's your wish. Now the drop-down menu presents a list of choices available, which are the folders, all notebooks, running, and files. So the folder section will select all the folders in the display and present a count of the folders in the small box. So as you can see here, we have 18 number of folders. Now all the notebook section will change the count of the number of notebooks and provide you with three options. So you can see here it has selected all the given notebooks, which are 18 in number, and you get the option to either duplicate the current notebook, you need to move it, view it, edit it, or delete it. Now the running section will select any running scripts. As you can see here, we have 0 running scripts and update the count to the number selected. Now the files section will select all the files in the notebook display and update the counts accordingly. So if you select the files here, we have 7 files. As you can see here, we have 7 files, some data sets, CSV files, and text files. Now the home button brings you back to the home screen of the notebook. So all you need to do is click on the Jupyter Notebook logo. It will bring you back to the Jupyter Notebook dashboard. Now, as you can see on the left hand side of every item is a checkbox, an icon, and the item's name. The checkbox is used to build a set of files to operate upon, and the icon is indicative of the type of the item. And in this case, all of the items are folder here. Coming down, we have the running notebooks, and finally we have certain files, which are the text files and the CSV files. Now, a typical workflow of any Jupyter notebook is to first of all create a notebook for the project or your data analysis, add your analysis step, coding and output, and surround your analysis with organization and presentation markdown to communicate an entire story. Now, interactive notebooks that include widgets and display modules would then be used by others by modifying parameters and the data to note the effects of their changes. Now, if we talk about security, Jupyter notebooks are created in order to be shared with other users, in many cases over the internet. However, Jupyter Notebook can execute arbitrary code and generate arbitrary code. This can be a problem if malicious aspects have been placed in the notebook. Now, the default security mechanism for Jupyter notebooks include raw HTML, which is always sanitized and checked for malicious coding. Another aspect is you cannot run external JavaScripts. Now, the cell contents, especially the HTML and the JavaScripts, are not trusted. It requires user validation to continue, and the output from any cell is not trusted. All other HTML or JavaScript is never trusted, and clearing the output will cause the notebook to become trusted when saved. Now, notebooks can also use a security digest to ensure the correct user is modifying the contents. So for that, what you need to do is a digest. What it does is takes into the account the entire contents of the notebook and a secret which is only known by the notebook creator. Now, this combination ensures that malicious coding is not going to be added to the notebook. So you can add security digest to notebook using the following command, which I have given here. So it's Jupyter, the profile, what you have selected, and inside what you need to do is security and notebook secret. So what you can do is replace the notebook secret with your part of the secret, and that will act as a key for the particular notebook. So what you need to do is share that particular key with all your colleagues or whoever you want to share that particular notebook with. And in that case, it keeps the notebook secured and away from other malicious coders and all. Another aspect of Jupyter is configuration. So you can configure some of the display parameters used when presenting notebooks. Now, these are configurable due to the use of product known as CodeMirror to present and modify the notebook. So CodeMirror, what it basically is, it is a JavaScript-based editor for the use within the web pages and notebooks. So what you do is CodeMirror. So as you can see here, CodeMirror is a versatile text editor implemented in JavaScript for the browser. So what it does is allow you to configure the options for Jupyter. So now let's execute some Python code and understand the notebook in a better way. Jupyter does not interact with your scripts as much as it executes your script and records the result. So I think this is how Jupyter notebooks have been extended to other languages besides Python, as it just takes a script, runs it against a particular language engine, and records the output from the engine, all the while not really knowing what kind of a script is being executed. Now the new window shows an empty cell for you to enter the Python code. Now what you need to do is under new, you select the Python 3, and what it will do is open a new notebook. Now this notebook is untitled, so let's give the new work area a name Python code. So as you can see, we have renamed this particular cell. Now autosave option should be on the next to the title. As you can see, last checkpoint a few days ago, unsaved changes. The autosave option is always on. What we do is with an accurate name, we can find the selection and this particular notebook very easily from the notebook homepage. So if you select your browser's home tab and refresh, you will find this new window name displayed here again. So if you just go to the notebook home, and as you can see, I mentioned it, Python codes. And under running also you have the Python codes here. So let's get back to the particular page or the notebook. One thing to note here that it has an item icon versus a folder icon. The automatically assigned extension, as you can see here, is IPYNB, the IPython node. And since the item is in a browser in a Jupyter environment, it is marked as running. And there is a file by that name in your directory as well. So if you go to your directory, let me go and check it. So as you can see, if you go into the users, here you can see we have the in-class projects, the Python codes. So you can see we automatically have that particular IPython notebook created in our working environment and the local disk space also. So if you open the IPYNB file in the text editor, you will see basic context of a Jupyter code. As you can see, if I'm opening it, the cells are empty, nothing is there. So let's type in some code here. So for example, I'm going to put in name equals Edureka. Next, what I'm going to do is provide subscribers that equals 700k. And to run this particular cell, what you need to do is click on the run icon. As you can see here, we have 1. So this is the first cell to be executed. In the second cell, we enter Python code that references the variables from the first cell. So as you can see here, we have print name has string subscribers. So let me just run this particular. So as you can see here, note that we have an output here that Edureka has 700k YouTube subscriber now. So it's more than 700k. Now, to know more about Jupyter and other technologies, what you can do is subscribe to our channel and get updates on the latest trending technologies. So note that Jupyter color codes your Python just as a decent editor would, and we have empty braces to the left of each code block. So as you can see here, if we execute the cell, the results are displayed in line. Now it's interesting that Jupyter keeps track of the output last generated in the saved version of the file and is a saved checkpoints. Now if you were to rerun your cells using the rerun or the run all, the output would be generated and saved via autosave. Now the cell number is incremented, and as you can see, if I rerun this, you see the cell number changed from 1 to 3, and if I rerun this, the cell number will change from 2 to 4. So what Jupyter does is keeps a track of the latest version of each cell. So similarly, if you were to close the browser tab, refresh the display in the home tab, you will find a new item we created, which is the Python code. Yeah, notebook saved, auto saved. As you can see here in the bracket, it has auto saved. So if we close this in the home button, you can see here we have Python codes. So as you can see, if we click it, it opens the same notebook. It has the previously displayed items will be always there, showing the outputs that we generated in the last run. Now that we have seen how Python works in Jupyter, including the underlying encoding, then how does Python access a large dataset or a dataset work in Jupyter? So let me create another new Python notebook. So what I'm going to do is name this as pandas. So from here, what we'll do is read in large dataset and compute some standard statistics of data. Now what we are interested in seeing how to use the pandas in Jupyter, how well the script performs, and what information is stored in the metadata, especially if it's a large dataset. So our Python script accesses the iris dataset here that's built into one of the Python packages. Now all we are looking into to do is to read in slightly large number of items and calculate some basic operations on the dataset. So first of all, what we need to do is from sklearn, import the dataset. So sklearn is scikit-learn, and it is another library of Python. It contains a lot of datasets for machine learning and all the algorithms which are present for machine learning and the datasets which are there. So our import was successful. So what we're going to do now is pull in the iris data. What we're going to do is iris underscore dataset equals dataset dot load underscore iris. Now this should do, and I'm sorry, it's datasets.load. So as you can see here, the number here is considered 3 now because in the second run we encountered an error. It was dataset, not dataset. So what we're gonna do is grab the first 2 columns of the data. So let's pretend x equals. If you press the tab, it automatically detects what you're gonna write as .datasets.data, and what we're gonna do is take the first 2 rows, comma. Now to run it from your keyboard, all you need to do is press Shift and Enter. So next what we're going to do is calculate some basic statistics. So what we're going to do is x underscore count equals x. We're going to use the length function. I said that we're going to use x dot flat. Similarly, we're going to see x min and x max and the mean. Now to display our results, what we're going to do is to display the results now. So as you can see, the count is 300. The minimum value is 3.8, the maximum value is 8.4, and the mean is 5.84333.
So let me connect you to the real life and tell you what all are the things which you can easily do using the concepts of machine learning. So you can easily get answer to the questions like which types of house lies in this segment, or what is the market value of this house, or is this a mail, a spam, or not a spam? Is there any fraud? Well, these were some of the questions you could ask to the machine. But for getting an answer to these, you need some algorithm. The machine need to train on the basis of some algorithm. Okay, but how will you decide which algorithm to choose and when? Okay, so the best option for us is to explore them one by one. So the first is classification algorithm, where the category is predicted using the data. If you have some question like, is this person a male or a female? Or is this male a spam or not a spam? Then these category of question would fall under the classification algorithm. Classification is a supervised learning approach in which the computer program learns from the input given to it and then uses this learning to classify new observation. Some examples of classification problems are speech recognition, handwriting recognition, biometric identification, document classification, etc. So next is the anomaly detection algorithm, where you identify the unusual data point. So what is anomaly detection? Well, it's a technique that is used to identify unusual patterns that do not conform to expected behavior, or you can say the outliers. It has many applications in business, like intrusion detection, like identifying strange patterns in the network traffic that could signal a hack, or system health monitoring, that is spotting a deadly tumor in the MRI scan. Or you can even use it for fraud detection, credit card transaction, or to deal with fault detection in operating environment. So next comes the clustering algorithm. You can use this clustering algorithm to group the data based on some similar condition. Now you can get answer to which type of houses lies in this segment or what type of customer buys this product. The clustering is the task of dividing the population or data points into a number of groups such that the data point in the same groups are more similar to other data points in the same group than those in the other groups. In simple words, the aim is to segregate groups with similar trait and assign them into cluster. Now this clustering is a task of dividing the population or data points into a number of groups such that the data points in the X group is more similar to the other data points in the same group rather than those in the other group. In other words, the aim is to segregate the groups with similar traits and assign them into different clusters. Let's understand this with an example. Suppose you're the head of a rental store and you wish to understand the preference of your customer to scale up your business. So is it possible for you to look at the detail of each customer and design a unique business strategy for each of them? Definitely not, right? But what you can do is to cluster all your customer, say into 10 different groups based on their purchasing habit, and you can use a separate strategy for customers in each of these 10 different groups. And this is what we call clustering. Next, we have regression algorithm, where the data itself is predicted. Question you may ask to this type of model is like, what is the market value of this house? Or is it going to rain tomorrow or not? So regression is one of the most important and broadly used machine learning and statistics tool. It allows you to make prediction from data by learning the relationship between the features of your data and some observed continuous valued response. Regression is used in a massive number of applications. You know what? Stock prices prediction can be done using regression. Now you know about different machine learning algorithm. How will you decide which algorithm to choose and when? So let's cover this part using a demo. So in this demo part, what we'll do, we'll create 6 different machine learning model and pick the best model and build the confidence such that it has the most reliable accuracy. So for our demo part, we'll be using the IRIS dataset. This dataset is quite very famous and is considered one of the best small project to start with. You can consider this as a hello world dataset for machine learning. So this dataset consists of 150 observation of iris flower. There are 4 columns of measurement of flowers in centimeters, the 5th column being the species of the flower observed. All the observed flowers belong to one of the 3 species of Iris setosa, Iris virginica, and Iris versicolor. Well, this is a good project because it is so well to understand. The attributes are numeric, so you have to figure out how to load and handle the data. It is a classification problem, thereby allowing you to practice with perhaps an easier type of supervised learning algorithm. It has only 4 attributes and 150 rows, meaning it is very small and can easily fit into the memory. And even all of the numeric attributes are in the same unit and the same scale. It means you do not require any special scaling or transformation to get started with. So let's start coding, and as I told earlier, for the demo part, I'll be using Anaconda with Python 3.0 installed on it. So when you install Anaconda, how your navigator would look like. So this is my homepage of my Anaconda navigator. On this, I'll be using the Jupyter Notebook, which is a web-based interactive computing notebook environment, which will help me to write and execute my Python codes on it. So let's hit the launch button and execute our Jupyter Notebook. So as you can see that my Jupyter Notebook is starting on localhost 8890. Okay, so this is my Jupyter Notebook. What I'll do here, I'll select new notebook Python 3. This is my environment where I can write and execute all my Python codes on it. So let's start by checking the version of the libraries. In order to make this video short and more interactive and more informative, I've already written the set of code. So let me just copy and paste it down. I'll explain you then one by one. So let's start by checking the version of the Python libraries. Okay, so there's the code. Let's just copy it, and let's paste it. Okay, first let me summarize things for you. What we are doing here, we are just checking the version of the different libraries. Starting with Python, we'll first check what version of Python we are working on. Then we'll check what are the version of SciPy we are using. Then NumPy, Matplotlib, then Panda, then scikit-learn. Okay, so let's execute the run button and see what are the various versions of the libraries which we are using. Hit the run. So we are working on Python 3.6.4, SciPy 1.0, NumPy 1.14, Matplotlib 2.12, Pandas 0.22, and scikit-learn of version 0.19. Okay, so these are the version which I'm using. Ideally, your version should be more recent or it should match. But don't worry if you lag few versions behind, as the APIs do not change so quickly. Everything in this tutorial will very likely still work for you. Okay, but in case you are getting an error, stop and try to fix that error. In case you are unable to find the solution for the error, feel free to reach out Edureka even after this class. Let me tell you this, if you're not able to run the script properly, you will not be able to complete this tutorial. Okay, so whenever you get a doubt, reach out to Edureka and just resolve it. Now if everything is working smoothly, then now it's the time to load the dataset. So as I said, I'll be using the Iris Flower dataset for this tutorial. But before loading the dataset, let's import all the modules, function, and the object which we are going to use in this tutorial. Same, I've already written the set of code, so let's just copy and paste them. Let's load all the libraries. So these are the various libraries which we'll be using in our tutorial. So everything should work fine without an error. If you get an error, just stop. You need to work on your SciPy environment before you continue any further. So I guess everything should work fine. Let's hit the run button and see. Okay, it worked. So let's now move ahead and load the data. We can load the data direct from the UCI machine learning repository. First of all, let me tell you, we are using Panda to load the data. Okay, so let's say my URL is this. So this is my URL for the UCI machine learning repository from where I'll be downloading the data set. Okay. Now what I'll do, I'll specify the name of each column when loading the data. This will help me later to explore the data. Okay. So I'll just copy and paste it down. Okay. So I'm defining a variable names which consist of various parameters including sepal length, sepal width, petal width, and class. So these are just the name of column from the data set. Okay. Now let's define the data set. So dataset equals panda.read_CSV. Inside that, we are defining URL and the names that is equal to name. As I already said, we'll be using Panda to load the data. All right. So we are using panda.read_CSV. So we are reading the CSV file, and inside that, from where that CSV is coming, from the URL. Which URL? So this is my URL. Okay. Our names equal names. It's just specifying the names of that various columns in that particular CSV file. Okay. So let's move forward and execute it. So even our data set is loaded. In case you have some network issues, just go ahead and download the Iris data file into your working directory and load it using the same method. But yeah, make sure that you change the URL to the local name or else you might get an error. Okay. Yeah, our data set is loaded. So let's move ahead and check our data set. Let's see how many columns or rows we have in our data set. Okay. So let's print the number of rows and columns in our data set. So our data set is dataset.shape. What this will do, it will just give you the numbers of total number of rows and total number of column, or you can say the total number of instances or attributes in your data set. Fine. So print dataset.shape. What you're getting? 150 and 5. So 150 is the total number of rows in your dataset and 5 is the total number of columns. Fine. So moving on ahead, what if I want to see the sample dataset? Okay. So let me just print the first 30 instances of the dataset. Okay. So print dataset.head. What I want is the first 30 instances. Fine. This will give me the first 30 result of my dataset. Okay. So when I hit the run button, what I'm getting is the first 30 result. Okay. 0 to 29. So this is how my sample dataset looks like. Sepal length, sepal width, petal length, petal width, and the class. Okay. So this is how our dataset looks like. Now let's move on and look at the summary of each attribute. What if I want to find out the count, mean, the minimum and the maximum values and some other percentiles as well? So what should I do then? For that, print dataset.describe. What it will give, let's see. So you can see that all the numbers are the same scales of similar range between 0 to 8 centimeters, right? The mean value, the standard deviation, the minimum value, the 25 percentile, 50 percentile, 75 percentile, the maximum value, all these values lies in the range between 0 to 8 centimeter. Okay. So what we just did is we just took a summary of each attribute. Now let's look at the number of instances that belong to each class. So for that, what we'll do, print dataset first of all. So let's print dataset and I want to group it, group by using class, and I want the size of it, size of each class. Fine. And let's hit the run. Okay, so what I want to do, I want to print what? Dataset. How I want to get it? I want it by class. So group by class. Okay, now I want the size of each class. Find the size of each class. So group by class dot size. Execute the run. So you can see that I have 50 instances of Iris setosa, 50 instances of Iris versicolor, and 50 instances of Iris virginica. Okay, all are of data type integer of base 64. Fine. So now we have a basic idea of our data. Now let's move ahead and create some visualization for it. So for this, we are going to create two different types of plot. First would be the univariate plot and the next would be the multivariate plot. So we'll be creating univariate plots to better understand about each attribute. And the next we'll be creating the multivariate plot to better understand the relationship between different attributes. Okay, so we start with some univariate plot. That is plot of each individual variable. So given that the input variables are numeric, we can create box and whiskers plot for it. Okay, so let's move ahead and create a box and whiskers plot. So dataset.plot, what kind I want? It's a box. Okay, and do I need a subplot? Yeah, I need subplots for that. So subplots equal true. What type of layout do I want? So my layout structure is 2 cross 2. Next, do I want to share my coordinates, x and y coordinates? No, I don't want to share it. So share x equal false. And even share y, that too equals false. Okay, so we have here dataset.plot kind equal box. My subplots is true, layout 2 cross 2. And then what I want to do it, I want to see it. So plot dot show, whatever I created, show it. Okay, execute it. Now this gives us a much clearer idea about the distribution of the input attribute. Now what if I had given the layout to 2 cross 2? Instead of that, I would have given it 4 cross 4. So what it will result? Just see. Fine. Everything would be printed in just one single row. Hold on guys, Arya has a doubt. He's asking that why we are using the share x and share y values. What are these? Why we have assigned false values to it? Okay, Arya, so in order to resolve this query, I need to show you what will happen if I give true values to them. Okay, so be with me. So share x equal true and share y that equals true. So let's see what result we'll get. You're getting it. The x and y coordinates are just shared among all the 4 visualization, right? So Arya, you can see that the sepal length and sepal width has y values ranging from 0.0 to 7.5, which are being shared among both the visualization. So is with the petal length, it has a shared value between 0.0 to 7.5. Okay, so that is why I don't want to share the value of x and y. So it's just giving us a cluttered visualization. So Arya, why I'm doing this? I'm just doing it because I don't want my x and y coordinates to be shared among any visualization. Okay, that is why my share x and share y value are false. Okay, let's execute it. So this is a pretty much clear visualization, which gives a clear idea about the distribution of the input attributes. Now, if you want, you can also create a histogram of each input variable to get a clear idea of the distribution. So let's create a histogram for it. So dataset.hist. Okay, I would need to see it. So plot.show. Let's see. So there's my histogram, and it seems that we have two input variables that have a Gaussian distribution. So this is useful to note as we can use the algorithms that can exploit this assumption. Okay, so next comes the multivariate plot. Now that we have created the univariate plot to understand about each attribute, let's move on and look at the multivariate plot and see the interaction between the different variables. So first, let's look at the scatter plot of all the attribute. This can be helpful to spot structured relationship between input variables. Okay, so let's create a scatter matrix. So for creating a scatter plot, we need scatter matrix, and we need to pass our data set into it. Okay, and then what I want to see it. So plot.show. So this is how my scatter matrix looks like. It's like that the diagonal grouping of some pair, right? So this suggests a high correlation and a predictable relationship. All right, this was our multivariate plot. Now let's move on and evaluate some algorithm. Now it's time to create some model of the data and estimate their accuracy on the basis of unseen data. Okay, so now we know all about our data set, right? We know how many instances and attributes are there in our data set. We know the summary of each attribute. Now I guess we have seen much about our data set. Now let's move on and create some algorithm and estimate their accuracy based on the unseen data. Okay, now what we'll do, we'll create some model of the data and estimate their accuracy based on some unseen data. Okay, so for that, first of all, let's create a validation data set. What is a validation data set? Validation data set is your training data set that will be using it to train our model. Fine. All right, so how we'll create a validation data set? For creating a validation data set, what we are going to do is we are going to split our data set into two parts. Okay, so the very first thing we'll do is to create a validation data set. So why do we even need a validation data set? So we need a validation data set to know that the model we created is any good. Later, what we'll do, we'll use the statistical method to estimate the accuracy of the model that we create on the unseen data. We also want a more concrete estimate of the accuracy of the best model on unseen data by evaluating it on the actual unseen data. Okay, confused? Let me simplify this for you. What we'll do, we'll split the loaded data into two parts. The first 80% of the data, we'll use it to train our model, and the rest 20% will hold back as the validation data set that will use it to verify our trained model. Okay, fine. So let's define an array. This is my array. What it will consist of? It will consist of all the values from the data set. So dataset dot values. Okay. Next, I'll define a variable x, which will consist of all the column from the array from 0 to 4, starting from 0 to 4. And the next variable y, which would consist of the array starting from this. So first of all, we'll define a variable x that will consist of the values in the array starting from the beginning 0 till 4. Okay, so these are the column which will include in the x variable. And for a y variable, I'll define it as a class or the output. So what I just need the fourth column, that is my class column. So I'll start it from the beginning and I just want the fourth column. Okay, now I'll define my validation size, validation underscore size. I'll define it as 0.20 and I'll use a seed. I'll define seed equals 6. So this method seed sets the integer starting value used in generating random number. Okay, I'll define the value of seed equals 6. I'll tell you what is the importance of it later on. Okay, so let me define first few variables such as x underscore train test, y underscore train, and y underscore test. Okay, so what we want to do is select some model. Okay, so model underscore selection. But before doing that, what we have to do is split our training data set into two halves. Okay, so dot train underscore test underscore split. What we want to split is the value of x and y. Okay, and my test size is equals to validation size, which is 0.20, correct? And my random state is equal to seed. So what the seed is doing here, it's helping me to keep the same randomness in the training and testing data set. Fine. So let's execute it and see what is our result. It's executed. Next, we'll create a test harness. For this, we'll use 10-fold cross-validation to estimate the accuracy. So what it will do, it will split our data set into 10 parts. Train on the 9 part and test on the 1 part. And this will repeat for all combination of train and test splits. Okay. So for that, let's define again my seed, that was 6 already defined, and scoring equals accuracy. Fine. So we are using the metric of accuracy to evaluate the model. So what is this? This is a ratio of number of correctly predicted instances divided by the total number of instances in the data set multiplied by 100, giving a percentage. Example, it's 98% accurate or 99% accurate, things like that. Okay. So we'll be using this scoring variable when we run the build and evaluate each model in the next step. So our next part is building model. Till now, we don't know which algorithm would be good for this problem or what configuration to use. So let's begin with 6 different algorithms. I'll be using logistic regression, linear discriminant analysis, k-nearest neighbor, classification and regression trees, naive Bayes, and code vector machine. Well, these algorithms which I'm using is a good mixture of simple linear or non-linear algorithms. In simple linears, which included the logistic regression and the linear discriminant analysis, or the non-linear part, which included the KNN algorithm, the CART algorithm, the naive Bayes, and the support vector machines. Okay, so we reset the random number seed before each run to ensure that evaluation of each algorithm is performed using exactly the same data splits. It ensures the results are directly comparable. Okay, so let me just copy and paste it. Okay. So what we are doing here, we are building 5 different types of model. We are building logistic regression, linear discriminant analysis, k-nearest neighbor, decision tree, Gaussian naive Bayes, and the support vector machine. Okay. Next, what we'll do, we'll evaluate model in each turn. Okay. So what is this? So we have 6 different model and accuracy estimation for each one of them. Now we need to compare the model to each other and select the most accurate of them all. So running this script, we saw the following result. So we can see some of the result on the screen. What is this? It is just the accuracy score using different set of algorithms. Okay, when we are using logistic regression, what is the accuracy rate? When we are using linear discriminant algorithm, what is the accuracy, and so and so. Okay, so from the output, it seems that LDA algorithm was the most accurate model that we tested. Now we want to get an idea of the accuracy of the model on our validation set or the testing data set. So this will give us an independent final check on the accuracy of the best model. It is always valuable to keep a testing data set for just in case you made a overfitting to the testing data set or you made a data leak. Both will result in an overly optimistic result. Okay. You can run the LDA model directly on the validation set and summarize the result as a final score, a confusion matrix, and a classification report.
Statistics and probability are essential because these disciples form the basic foundation of all machine learning algorithms, deep learning, artificial intelligence, and data science. In fact, mathematics and probability is behind everything around us. From shapes, patterns, and colors to the count of petals in a flower, mathematics is embedded in each and every aspect of our lives. So I'm going to go ahead and discuss the agenda for today with you all. We're going to begin this session by understanding what is data. After that, we'll move on and look at the different categories of data like quantitative and qualitative data. Then we'll discuss what exactly statistics is, the basic terminologies in statistics, and a couple of sampling techniques. Once we're done with that, we'll discuss the different types of statistics which involve descriptive and inferential statistics. Then in the next session, we'll mainly be focusing on descriptive statistics. Here we'll understand the different measures of center, measures of spread, information gain, and entropy. We'll also understand all of these measures with the help of a use case. And finally, we'll discuss what exactly a confusion matrix is. Once we've covered the entire descriptive statistics module, we'll discuss the probability module. Here we'll understand what exactly probability is, the different terminologies in probability. We'll also study the different probability distributions. Then we'll discuss the types of probability, which include marginal probability, joint, and conditional probability. Then we'll move on and discuss a use case wherein we'll see examples that show us how the different types of probability work. And to better understand Bayes' theorem, we'll look at a small example. Also, I forgot to mention that at the end of the descriptive statistics module, we'll be running a small demo in the R language. So for those of you who don't know much about R, I'll be explaining every line in depth. But if you want to have a more in-depth understanding about R, I'll leave a couple of blogs and a couple of videos in the description box. You all can definitely check out that content. Now, after we've completed the probability module, we'll discuss the inferential statistics module. We'll start this module by understanding what is point estimation. We'll discuss what is confidence interval and how you can estimate the confidence interval. We'll also discuss margin of error, and we'll understand all of these concepts by looking at a small use case. We'll finally end the inferential statistic module by looking at what hypothesis testing is. Hypothesis testing is a very important part of inferential statistics. So we'll end the session by looking at a use case that discusses how hypothesis testing works. And to sum everything up, we'll look at a demo that explains how inferential statistics works. Alright, so guys, there's a lot to cover today. So let's move ahead and take a look at our first topic, which is what is data. Now, this is a quite simple question. If I ask any of you what is data, you'll say that it's a set of numbers or some sort of documents that I've stored in my computer. Now, data is actually everything. All right, look around you. There is data everywhere. Each click on your phone generates more data than you know. Now, this generated data provides insights for analysis and helps us make better business decisions. This is why data is so important. To give you a formal definition, data refers to facts and statistics collected together for reference or analysis. Alright, this is the definition of data in terms of statistics and probability. So as we know, data can be collected, it can be measured and analyzed, it can be visualized by using statistical models and graphs. Now, data is divided into two major subcategories. Alright. So first we have qualitative data and quantitative data. These are the two different types of data. Under qualitative data, we have nominal and ordinal data, and under quantitative data, we have discrete and continuous data. Now let's focus on qualitative data. Now this type of data deals with characteristics and descriptors that can't be easily measured but can be observed subjectively. Now, qualitative data is further divided into nominal and ordinal data. So, nominal data is any sort of data that doesn't have any order or ranking. Okay. An example of nominal data is gender. Now, there is no ranking in gender. There's only male, female, or other, right? There is no 1, 2, 3, 4, or any sort of ordering in gender. Race is another example of nominal data. Now, ordinal data is basically an ordered series of information. Okay, let's say that you went to a restaurant. Okay, your information is stored in the form of customer ID. All right, so basically you are represented with a customer ID. Now, you would have rated their service as either good or average. All right, that's how ordinal data is. And similarly, they'll have a record of other customers who visit the restaurant along with their ratings. All right. So any data which has some sort of sequence or some sort of order to it is known as ordinal data. All right. So guys, this is pretty simple to understand. Now let's move on and look at quantitative data. So quantitative data basically deals with numbers and things. Okay. You can understand that by the word quantitative itself. Quantitative is basically quantity, right? So it deals with numbers. It deals with anything that you can measure objectively. All right. So there are two types of quantitative data. There is discrete and continuous data. Now, discrete data is also known as categorical data, and it can hold a finite number of possible values. Now, the number of students in a class is a finite number. All right, you can't have infinite number of students in a class. Let's say in your 5th grade, there were 100 students in your class. All right, there weren't infinite number, but there was a definite finite number of students in your class. Okay, that's discrete data. Next, we have continuous data. Now, this type of data can hold infinite number of possible values. Okay, so when you say weight of a person is an example of continuous data, what I mean to say is my weight can be 50 kgs, or it can be 50.1 kgs, or it can be 50.001 kgs, or 50.0001, or it's 50.023, and so on, right? There are infinite number of possible values. Right? So this is what I mean by continuous data. All right, this is the difference between discrete and continuous data. And also I'd like to mention a few other things over here. Now, there are a couple of types of variables as well. All right, we have a discrete variable and we have a continuous variable. Discrete variable is also known as a categorical variable. All right, it can hold values of different categories. Let's say that you have a variable called a message. And there are two types of values that this variable can hold. Let's say that your message can either be a spam message or a non-spam message. Okay, that's when you call a variable as discrete or categorical variable. All right, because it can hold values that represent different categories of data. Now, continuous variables are basically variables that can store infinite number of values. So the weight of a person can be denoted as a continuous variable. All right, let's say there is a variable called weight and it can store infinite number of possible values. That's why we'll call it a continuous variable. So guys, basically variable is anything that can store a value, right? So if you associate any sort of data with a variable, then it will become either discrete variable or continuous variable. There is also dependent and independent type of variables. Now we won't discuss all of that in depth because that's pretty understandable. I'm sure all of you know what is independent variable and dependent variable, right? Dependent variable is any variable whose value depends on any other independent variable. So guys, that much knowledge I expect all of you to have. All right. So now let's move on and look at our next topic, which is what is statistics. Now coming to the formal definition of statistics, statistics is an area of applied mathematics which is concerned with data collection, analysis, interpretation, and presentation. Now, usually when I speak about statistics, people think statistics is all about analysis. But statistics has other parts to it. It has data collection is also a part of statistics. Data interpretation, presentation, visualization, all of this comes into statistics. All right, you're going to use statistical methods to visualize data, to collect data, to interpret data. All right. So the area of mathematics deals with understanding how data can be used to solve complex problems. Okay. Now I'll give you a couple of examples that can be solved by using statistics. Okay, let's say that your company has created a new drug that may cure cancer. How would you conduct a test to confirm the drug's effectiveness? Now, even though this sounds like a biology problem, this can be solved with statistics. All right, you'll have to create a test which can confirm the effectiveness of the drug. All right, this is a common problem that can be solved using statistics. Let me give you another example. You and a friend are at a baseball game, and out of the blue, he offers you a bet that neither team will hit a home run in that game. Should you take the bet? All right, here you'll just discuss the probability of whether you'll win or lose. All right, this is another problem that comes under statistics. Let's look at another example. The latest sales data has just come in, and your boss wants you to prepare a report for management on places where the company could improve its business. What should you look for and what should you not look for? Now, this problem involves a lot of data analysis. You'll have to look at the different variables that are causing your business to go down, or that you have to look at a few variables that are increasing the performance of your models and thus growing your business. All right. So this involves a lot of data analysis, and the basic idea behind data analysis is to use statistical techniques in order to figure out the relationship between different variables or different components in your business. Okay, so now let's move on and look at our next topic, which is basic terminologies in statistics. Now, before you dive deep into statistics, it is important that you understand the basic terminologies used in statistics. The two most important terminologies in statistics are population and sample. So throughout the statistics course or throughout any problem that you're trying to solve with statistics, you will come across these two words, which is population and sample. Now, population is a collection or a set of individuals or objects or events whose properties are to be analyzed. Okay, so basically you can refer to population as a subject that you're trying to analyze. Now, a sample is just like the word suggests, it's a subset of the population. So you have to make sure that you choose the sample in such a way that it represents the entire population. All right, it shouldn't focus at one part of the population. Instead, it should represent the entire population. That's how your sample should be chosen. So a well-chosen sample will contain most of the information about a particular population parameter. Now you must be wondering, how can one choose a sample that best represents the entire population? Now, sampling is a statistical method that deals with the selection of individual observations within a population. So sampling is performed in order to infer statistical knowledge about a population. All right, if you want to understand the different statistics of a population, like the mean, the median, the mode, or the standard deviation, or the variance of a population, then you're going to perform sampling. All right, because it's not reasonable for you to study a large population and find out the mean, median, and everything else. So why is sampling performed? You might ask, what is the point of sampling? We can just study the entire population. Now, guys, think of a scenario wherein you're asked to perform a survey about the eating habits of teenagers in the US. So, at present, there are over 42 million teens in the US, and this number is growing as we are speaking right now, correct? Is it possible to survey each of these 42 million individuals about their health? Is it possible? Well, it might be possible, but this will take forever to do. Now, obviously, it's not. It's not reasonable to go around knocking each door and asking for what does your teenage son eat and all of that. All right, this is not very reasonable. That's why sampling is used. It's a method wherein a sample of the population is studied in order to draw inference about the entire population. So it's basically a shortcut to studying the entire population. Instead of taking the entire population and finding out all the solutions, you're just going to take a part of the population that represents the entire population, and you're going to perform all your statistical analysis, your inferential statistics on that small sample. All right. And that sample basically represents the entire population. All right. So I'm sure I've made this clear to you all, what is sample and what is population. Now, there are two main types of sampling techniques that I'll discuss today. We have probability sampling and non-probability sampling. Now, in this video, we'll only be focusing on probability sampling techniques because non-probability sampling is not within the scope of this video. All right, we'll only discuss the probability part because we're focusing on statistics and probability, correct? Now again, under probability sampling, we have three different types. We have random sampling, systematic, and stratified sampling. All right. And just to mention the different types of non-probability samplings, we have snowball, quota, judgment, and convenience sampling. All right. Now guys, in this session, I'll only be focusing on probability. So let's move on and look at the different types of probability sampling. So what is probability sampling? It is a sampling technique in which samples from a large population are chosen by using the theory of probability. All right. So there are three types of probability sampling. All right. First, we have the random sampling. Now, in this method, each member of the population has an equal chance of being selected in the sample. All right, so each and every individual or each and every object in the population has an equal chance of being a part of the sample. That's what random sampling is all about. Okay, you're randomly going to select any individual or any object. So this way, each individual has an equal chance of being selected. Correct? Next, we have systematic sampling. Now, in systematic sampling, every nth record is chosen from the population to be a part of the sample. All right. Now, refer this image that I've shown over here. Out of these 6 groups, every second group is chosen as a sample. Okay, so every second record is chosen here. And this is how systematic sampling works. Okay, you're randomly selecting the nth record and you're going to add that to your sample. Next, we have stratified sampling. Now, in this type of technique, a stratum is used to form samples from a large population. So what is a stratum? A stratum is basically a subset of the population that shares at least one common characteristics. So let's say that your population has a mix of both male and female. So you can create two stratums out of this. One will have only the male subset and the other will have the female subset. All right, this is what stratum is. It is basically a subset of the population that shares at least one common characteristics. All right, in our example, it is gender. So after you've created a stratum, you're going to use random sampling on these stratums and you're going to choose a final sample. So random sampling meaning that all of the individuals in each of the stratum will have an equal chance of being selected in the sample. Correct? So guys, these were the 3 different types of sampling techniques. Now let's move on and look at our next topic, which is the different types of statistics. So after this, we'll be looking at the more advanced concepts of statistics. All right, so far we discussed the basics of statistics, which is basically what is statistics, the different sampling techniques, and the terminologies in statistics. All right, now we look at the different types of statistics. So there are two major types of statistics: descriptive statistics and inferential statistics. In today's session, we'll be discussing both of these types of statistics in depth. All right, we'll also be looking at a demo which I'll be running in the R language in order to make you understand what exactly descriptive and inferential statistics is. So guys, we're just going to look at the basics, so don't worry if you don't have much knowledge. I'm explaining everything from the basic level. All right. So guys, descriptive statistics is a method which is used to describe and understand the features of specific data set by giving a short summary of the data. Okay, so it is mainly focused upon the characteristics of data. It also provides a graphical summary of the data. Now, in order to make you understand what descriptive statistics is, let's suppose that you want to gift all your classmates a t-shirt. So to study the average shirt size of a student in a classroom, so if you were to use descriptive statistics to study the average shirt size of students in your classroom, then what you would do is you would record the shirt size of all students in the class, and then you would find out the maximum, minimum, and average shirt size of the class. Okay, so coming to inferential statistics makes inferences and predictions about a population based on the sample of data taken from the population. Okay, so in simple words, it generalizes a large data set and it applies probability to draw a conclusion. Okay, so it allows you to infer data parameters based on a statistical model by using sample data. So if we consider the same example of finding the average shirt size of students in a class, in inferential statistics, you will take a sample set of the class, which is basically a few people from the entire class. All right. You already have had grouped the class into large, medium, and small. All right. In this method, you basically build a statistical model and expand it for the entire population in the class. So guys, that was a brief understanding of descriptive and inferential statistics. So that's the difference between descriptive and inferential. Now, in the next section, we'll go in depth about descriptive statistics. All right. So let's discuss more about descriptive statistics. So like I mentioned earlier, descriptive statistics is a method that is used to describe and understand the features of a specific data set by giving short summaries about the sample and measures of the data. There are two important measures in descriptive statistics. We have measure of central tendency, which is also known as measure of center, and we have measures of variability. This is also known as measures of spread. So measures of center include mean, median, and mode. Now, what is measures of center? Measures of the center are statistical measures that represent the summary of a data set. Okay, the three main measures of center are mean, median, and mode. Coming to measures of variability or measures of spread, we have range, interquartile range, variance, and standard deviation. All right. So now let's discuss each of these measures in a little more depth, starting with the measures of center. Now, I'm sure all of you know what the mean is. Mean is basically the measure of the average of all the values in a sample. Okay, so it's basically the average of all the values in a sample. How do you measure the mean? I hope all of you know how the mean is measured. If there are 10 numbers and you want to find the mean of these 10 numbers, all you have to do is you have to add up all the 10 numbers and you have to divide it by 10. 10 here represents the number of samples in your data set. All right, since we have 10 numbers, we're going to divide this by 10. All right, this will give us the average or the mean. So to better understand the measures of central tendency, let's look at an example. Now the data set over here is basically the cars data set and it contains a few variables. All right, it has something known as cars. It has mileage per gallon, cylinder type, displacement, horsepower, and real axle ratio. All right, all of these measures are related to cars. Okay. So what you're going to do is you're going to use descriptive analysis and you're going to analyze each of the variables in the sample data set for the mean, standard deviation, median, mode, and so on. So let's say that you want to find out the mean or the average horsepower of the cars among the population of cars. Like I mentioned earlier, what you'll do is you'll check the average of all the values. So in this case, we'll take the sum of the horsepower of each car and we'll divide that by the total number of cars. Okay, that's exactly what I've done here in the calculation part. So this 110 basically represents the horsepower for the first car. Alright, similarly, I've just added up all the values of horsepower for each of the cars and I've divided it by 8. Now 8 is basically the number of cars in our data set. Alright, so 103.625 is what our mean is or the average of horsepower is. Alright, now let's understand what median is with an example. Okay, so to define median, median is basically a measure of the central value of the sample set is called the median. All right, you can say that it is a middle value. So if we want to find out the center value of the mileage per gallon among the population of cars, first what we'll do is we'll arrange the MPG values in ascending or descending order and choose a middle value. All right, in this case, since we have 8 values, right, we have 8 values, which is an even entry. So whenever you have even number of data points or samples in your data set, then you're going to take the average of the two middle values. If we had 9 values over here, we can easily figure out the middle value and choose that as a median. But since there are even number of values, we're going to take the average of the two middle values. All right. So 22.8 and 23 are my two middle values, and I'm taking the mean of those two, and hence I get 22.9, which is my median. All right. Lastly, let's look at how mode is calculated. So what is mode? Now, the value that is most recurrent in the sample set is known as mode, or basically the value that occurs most often. Okay, that is known as mode. So let's say that we want to find out the most common type of cylinder among the population of cars. All we have to do is we will check the value which is repeated the most number of times. Here we can see that the cylinders come in two types. We have cylinder of type 4 and cylinder of type 6, right? So take a look at the data set. You can see that the most recurring value is 6, right? We have 1, 2, 3, 4, and 5. We have 5, 6, and we have 1, 2, 3. Yeah, we have 3, 4 type cylinders and 5, 6 type cylinders. So basically we have 3, 4 type cylinders and we have 5, 6 type cylinders. Alright, so our mode is going to be 6 since 6 is more recurrent than 4. So guys, those were the measures of the center or the measures of central tendency. Now let's move on and look at the measures of the spread. Alright, now what is the measure of spread? A measure of spread, sometimes also called as measure of dispersion, is used to describe the variability in a sample or population. Okay, you can think of it as some sort of deviation in the sample. Alright, so you measure this with the help of the different measure of spreads. We have range, interquartile range, variance, and standard deviation. Now, range is pretty self-explanatory, right? It is the given measure of how spread apart the values in a data set are. The range can be calculated as shown in this formula. So you're basically going to subtract the maximum value in your data set from the minimum value in your data set. That's how you calculate the range of the data. All right. Next, we have interquartile range. So before we discuss interquartile range, let's understand what a quartile is. Alright, so quartiles basically tell us about the spread of a data set by breaking the data set into different quartiles. Okay, just like how the median breaks the data into two parts, the quartile will break it into different quartiles. So to better understand how quartile and interquartile are calculated, let's look at a small example. Now, this data set basically represents the marks of 100 students ordered from the lowest to the highest scores. Alright, so the quartiles lie in the following ranges. Now, the first quartile, which is also known as Q1, it lies between the 25th and the 26th observation. Alright, so if you look at this, I've highlighted the 25th and the 26th observation. So how you can calculate Q1 or first quartile is by taking the average of these two values. Alright, since both the values are 45, when you add them up and divide them by 2, you'll still get 45. Now, the second quartile or Q2 is between the 50th and the 51st observation. So you're going to take the average of 58 and 59 and you'll get a value of 58.5. Now, this is my second quarter. The third quartile or Q3 is between the 75th and the 76th observation. Here again, you'll take the average of the two values, which is the 75th value and the 76th value. All right, and you'll get a value of 71. All right, so guys, this is exactly how you calculate the different quartiles. Now let's look at what is interquartile range. So IQR or the interquartile range is a measure of variability based on dividing a dataset into quartiles. Now the interquartile range is calculated by subtracting the Q1 from Q3. So basically Q3 minus Q1 is your IQR. So your IQR is your Q3 minus Q1. Alright. Now this is how each of the quartiles are. Each quartile represents a quarter, which is 25%. Alright. So guys, I hope all of you are clear with interquartile range and what are quartiles. Now let's look at variance. Now variance is basically a measure that shows how much a random variable differs from its expected value. Okay, it's basically the variance in any variable. Now variance can be calculated by using this formula. Right here, X basically represents any data point in your data set. N is the total number of data points in your data set, and X bar is basically the mean of data points. Alright, this is how you calculate variance. Variance is basically computing the squares of deviations. Okay, that's why it says S squared there. Now let's look at what is deviation. Deviation is just the difference between each element from the mean. Okay, so it can be calculated by using this simple formula where xi basically represents a data point and mu is the mean of the population. Alright, this is exactly how you calculate deviation. Now, population variance and sample variance are very specific to whether you're calculating the variance in your population dataset or in your sample dataset. That's the only difference between population and sample variance. So the formula for population variance is pretty explanatory. So xi is basically each data point, mu is the mean of the population, n is the number of samples in your dataset. All right. Now let's look at sample variance. Now, sample variance is the average of square differences from the mean. Alright, here xi is any data point or any sample in your data set. X bar is the mean of your sample. Alright, it's not the mean of your population. It's the mean of your sample. And if you notice, n here is a smaller n, it's the number of data points in your sample. And this is basically the difference between sample and population variance. I hope that is clear. Coming to standard deviation, it is the measure of dispersion of a set of data from its mean. Alright, so it's basically the deviation from your mean. That's what standard deviation is. Now, to better understand how the measures of spread are calculated, let's look at a small use case. So let's say Daenerys has 20 dragons. They have the numbers 9, 2, 5, 4 and so on as shown on the screen. What you have to do is you have to work out the standard deviation. Alright, in order to calculate the standard deviation, you need to know the mean, right? So first you're going to find out the mean of your sample set. So how do you calculate the mean? You add all the numbers in your data set divided by the total number of samples in your data set. So you get a value of 7 here. Then you calculate the RHS of your standard deviation formula. Alright, so from each data point, you're going to subtract the mean and you're going to square that. Alright, so when you do that, you'll get the following result. You'll basically get this 425, 4, 9, 25 and so on. So finally, you'll just find the mean of these squared differences. Alright, so your standard deviation will come up to 2.983 once you take the square root. So guys, this is pretty simple. It's a simple mathematic technique. All you have to do is you have to substitute the values in the formula. Alright, I hope this was clear to all of you. Now let's move on and discuss the next topic, which is information gain and entropy. Now this is one of my favorite topics in statistics. It's very interesting. And this topic is mainly involved in machine learning algorithms like decision trees and random forest. All right, it's very important for you to know how information gain and entropy really work and why they're so essential in building machine learning models. We'll focus on the statistic parts of information gain and entropy. And after that, we'll discuss a use case and see how information gain and entropy is used in decision trees. So for those of you who don't know what a decision tree is, it is basically a machine learning algorithm. You don't have to know anything about this. I'll explain everything in depth, so don't worry. Now let's look at what exactly entropy and information gain is. Now guys, entropy is basically the measure of any sort of uncertainty that is present in the data. Alright, so it can be measured by using this formula. So here S is the set of all instances in the data set or all the data items in the data set. N is the different type of classes in your data set. Pi is the event probability. Now this might seem a little confusing to you all, but when we go through the use case, you'll understand all of these terms even better. Alright. Coming to information gain, as the word suggests, information gain indicates how much information a particular feature or a particular variable gives us about the final outcome. Okay, it can be measured by using this formula. So again, here h of S is the entropy of the whole data set S. Sj is the number of instances with the j value of an attribute A. S is the total number of instances in the data set. V is the set of distinct values of an attribute A. H of Sj is the entropy of subset of instances, and H of A, S is the entropy of an attribute A. Even though this seems confusing, I'll clear out the confusion. Alright, let's discuss a small problem statement where we'll understand how information gain and entropy is used to study the significance of a model. So like I said, information gain and entropy are very important statistical measures that let us understand the significance of a predictive model. Okay, to get a more clear understanding, let's look at a use case. Alright, now suppose we're given a problem statement. Alright, the statement is that you have to predict whether a match can be played or not by studying the weather conditions. So the predictor variables here are outlook, humidity, wind. Day is also a predictor variable. The target variable is basically play. Alright, the target variable is the variable that you're trying to predict. Okay. Now the value of the target variable will decide whether or not a game can be played. Alright, so that's why the play has two values. It has no and yes. No meaning that the weather conditions are not good and therefore you cannot play the game. Yes meaning that the weather conditions are good and suitable for you to play the game. Alright, so that was a problem statement. I hope the problem statement is clear to all of you. Now to solve such a problem, we make use of something known as decision trees. So guys, think of an inverted tree and each branch of the tree denotes some decision. Alright, each branch is known as the branch node, and at each branch node you're going to take a decision in such a manner that you'll get an outcome at the end of the branch. Alright, now this figure here basically shows that out of 14 observations, 9 observations result in a yes, meaning that out of 14 days the match can be played only on 9 days. Alright, so here if you see on day 1, day 2, day 8, day 9 and day 11, the outlook has been sunny. Alright, so basically we're trying to cluster our data set depending on the outlook. So when the outlook is sunny, this is our data set. When the outlook is overcast, this is what we have. And when the outlook is rain, this is what we have. Alright, so when it is sunny, we have 2 yeses and 3 no's. Okay, when the outlook is overcast, we have all 4 as yeses, meaning that on the 4 days when the outlook was overcast, we can play the game. Alright, now when it comes to rain, we have 3 yeses and 2 no's. Alright, so if you notice here, the decision is being made by choosing the outlook variable as the root node. Okay, so the root node is basically the topmost node in a decision tree. Now what we've done here is we've created a decision tree that starts with the outlook node. Alright, then you're splitting the decision tree further depending on other parameters like sunny, overcast and rain. Alright, now like we know that outlook has 3 values: sunny, overcast and rain. So let me explain this in a more in-depth manner. Okay, so what you're doing here is you're making the decision tree by choosing the outlook variable at the root node. The root node is basically the topmost node in a decision tree. Now the outlook node has 3 branches coming out from it, which is sunny, overcast and rain. So basically outlook can have 3 values. Either it can be sunny, it can be overcast or it can be rainy. Okay, now these 3 values are assigned to the immediate branch nodes, and for each of these values, the possibility of play is equal to yes is calculated. So the sunny and the rain branches will give you an impure output, meaning that there is a mix of yes and no, right? There are 2 yeses here, 3 no's here. There are 3 yeses here and 2 no's over here. But when it comes to the overcast variable, it results in a 100% pure subset. Alright, this shows that the overcast variable will result in a definite and certain output. This is exactly what entropy is used to measure. Alright, it calculates the impurity or the uncertainty. Alright, so the lesser the uncertainty or the entropy of a variable, more significant is that variable. So when it comes to overcast, there's literally no impurity in the data set. It is a 100% pure subset, right? So we want variables like these in order to build a model. All right. Now we don't always get lucky and we don't always find variables that will result in pure subsets. That's why we have the measure entropy. So the lesser the entropy of a particular variable, the more significant that variable will be. So in a decision tree, the root node is assigned the best attribute so that the decision tree can predict the most precise outcome. Meaning that on the root node, you should have the most significant variable. All right, that's why we've chosen outlook. All right, now some of you might ask me, why haven't you chosen overcast? Now guys, the overcast is not a variable. It is a value of the outlook variable. All right, that's why we've chosen outlook here, because it has a 100% pure subset, which is overcast. All right, now the question in your head is, how do I decide which variable or attribute best splits the data? Now right now I know I looked at the data and I told you that here we have a 100% pure subset. But what if it's a more complex problem and you're not able to understand which variable will best split the data? So guys, when it comes to decision trees, information gain and entropy will help you understand which variable will best split the data set, all right, or which variable you have to assign to the root node. Because whichever variable is assigned to the root node, it will best split the data set, and it has to be the most significant variable. All right. So how we can do this is we need to use information gain and entropy. So from the total of the 14 instances that we saw, 9 of them said yes, and 5 of the instances said no, that you cannot play on that particular day. All right, so how do you calculate the entropy? So this is the formula. You just substitute the values in the formula. So when you substitute the values in the formula, you'll get a value of 0.940. All right, this is the entropy, or this is the uncertainty of the data present in our sample. Now, in order to ensure that we choose the best variable for the root node, let us look at all the possible combinations that you can use on the root node. Okay, so these are all the possible combinations. You can either have outlook, you can have windy, humidity, or temperature. Okay, these are our 4 variables, and you can have any one of these variables as your root node. But how do you select which variable best fits the root node? That's what we are going to see by using information gain and entropy. So guys, now the task at hand is to find the information gain for each of these attributes. All right, so for outlook, for windy, for humidity, and for temperature, we're going to find out the information gain. All right. Now a point to remember is that the variable that results in the highest information gain must be chosen, because it will give us the most precise and output information. All right. So the information gain for attribute windy, we'll calculate that first. Here we have 6 instances of true and 8 instances of false. Okay, so when you substitute all the values in the formula, you'll get a value of 0.048. So we get a value of 0.048. Now this is a very low value for information gain. All right, so the information that you're going to get from windy attribute is pretty low. So let's calculate the information gain of attribute outlook. Alright, so from the total of 14 instances, we have 5 instances which say sunny, 4 instances which are overcast, and 5 instances which are rainy. Alright, for sunny, we have 3 yeses and 2 no's. For overcast, we have all the 4 as yes. For rainy, we have 3 yes and 2 no's. Okay, so when you calculate the information gain of the outlook variable, you'll get a value of 0.247. Now compare this to the information gain of the windy attribute. This value is actually pretty good, right? We have 0.247, which is a pretty good value for information gain. Now let's look at the information gain of attribute humidity. Now over here we have 7 instances which say high and 7 instances which say normal, right? And under the high branch node, we have 3 instances which say yes, and the rest 4 instances which say no. Similarly, under the normal branch, we have 1, 2, 3, 4, 5, 6, 7 instances which say yes, and 1 instance which says no. All right. So when you calculate the information gain for the humidity variable, you're going to get a value of 0.151. Now this is also a pretty decent value, but when you compare it to the information gain of the attribute outlook, it is less, right? Now let's look at the information gain of attribute temperature. All right, so the temperature can hold, repeat. So basically the temperature attribute can hold hot, mild, and cool. Okay, under hot we have 2 instances which says yes and 2 instances for no. Under mild we have 4 instances of yes and 2 instances of no. And under cool we have 3 instances of yes and 1 instance of no. Alright, now when you calculate the information gain for this attribute, you'll get a value of 0.029, which is again very less. So what you can summarize from here is, if we look at the information gain for each of these variables, we'll see that for Outlook we have the maximum gain. Alright, we have 0.247, which is the highest information gain value. And you must always choose a variable with the highest information gain to split the data at the root node. So that's why we assign the Outlook variable at the root node. Alright, so guys, I hope this use case was clear. If any of you have doubts, please keep commenting those doubts. Now let's move on and look at what exactly a confusion matrix is. Now the confusion matrix is the last topic for descriptive statistics. Alright, after this I'll be running a short demo where I'll be showing you how you can calculate mean, median, mode, and standard deviation, variance, and all of those values by using R. Okay, so let's talk about confusion matrix. Now guys, what is a confusion matrix? Now don't get confused, this is not any complex topic. Now a confusion matrix is a matrix that is often used to describe the performance of a model. Alright, and this is specifically used for classification models or a classifier. And what it does is it will calculate the accuracy, or it will calculate the performance of your classifier by comparing your actual results and your predicted results. Alright, so this is what it looks like: true positive plus true negative and all of that. Now this is a little confusing. I'll get back to what exactly true positive, true negative, and all of this stands for. For now, let's look at an example and let's try and understand what exactly confusion matrix is. So guys, I made sure that I put examples after each and every topic because it's important you understand the practical part of statistics. Alright, statistics has literally nothing to do with theory. You need to understand how calculations are done in statistics. Okay, so here what I've done is, now let's look at a small use case. Okay, let's consider that you're given data about 165 patients, out of which 105 patients have a disease and the remaining 50 patients don't have a disease. Okay, so what you're going to do is you'll build a classifier that predicts by using these 165 observations. You'll feed all of these 165 observations to your classifier and it will predict the output every time a new patient's detail is fed to the classifier. Right? Now, out of these 165 cases, let's say that the classifier predicted yes 110 times and no 55 times. Alright? So yes basically stands for yes, the person has a disease, and no stands for no, the person does not have a disease. Alright? That's pretty self-explanatory. But yeah, so it predicted that 110 times the patient has a disease and 55 times that no, the patient doesn't have a disease. However, in reality, only 105 patients in the sample have the disease and 60 patients do not have the disease, right? So how do you calculate the accuracy of your model? You basically build the confusion matrix, all right? This is how the matrix looks like. N basically denotes the total number of observations that you have, which is 165 in our case. Actual denotes the actual values in the data set, and predicted denotes the predicted values by the classifier. So the actual value is no here and the predicted value is no here. So your classifier was correctly able to classify 50 cases as no. Alright, since both of these are no, so 50 it was correctly able to classify, but 10 of these cases it incorrectly classified, meaning that your actual value here is no, but your classifier predicted it as yes. Alright, that's why there's 10 over here. Similarly, it wrongly predicted that 5 patients do not have diseases, whereas they actually did have diseases, and it correctly predicted 100 patients which had the disease. All right, I know this is a little bit confusing, but if you look at these values, no, 50, meaning that it correctly predicted 50 values. No, yes means that it wrongly predicted yes for the values that it was supposed to predict no. All right. Now, what exactly is this true positive, true negative, and all of that? I'll tell you what exactly it is. So, true positive are the cases in which we predicted a yes and they do not actually have the disease. All right. So, it is basically this value. All right. We predicted a yes here, even though they did not have the disease. So, we have 10 true positives, right? Similarly, true negative is we predicted no and they don't have the disease, meaning that this is correct. False positive is we predicted yes, but they do not actually have the disease. All right, this is also known as type 1 error. False negative is we predicted no, but they actually do not have the disease. So, guys, basically, false negative and true negatives are basically correct classifications. All right. So this was confusion matrix and I hope this concept is clear. Again, guys, if you have doubts, please comment your doubts in the comment section. So guys, that was the entire descriptive statistics module. And now we'll discuss about probability. Okay, so before we understand what exactly probability is, let me clear out a very common misconception. People often tend to ask me this question, what is the relationship between statistics and probability? So probability and statistics are related fields, all right? So probability is a mathematical method used for statistical analysis. Therefore, we can say that probability and statistics are interconnected branches of mathematics that deal with analyzing the relative frequency of events. So they're very interconnected fields, and probability makes use of statistics and statistics makes use of probability. All right, they're very interconnected fields. So that is the relationship between statistics and probability. Now let's understand what exactly is probability. So probability is the measure of how likely an event will occur. To be more precise, it is the ratio of desired outcome to the total outcomes. Now the probability of all outcomes always sum up to 1. Now the probability will always sum up to 1. Probability cannot go beyond 1. Okay, so either your probability can be 0 or it can be 1, or it can be in the form of decimals like 0.52 or 0.55, or it can be in the form of 0.5, 0.7, 0.9, but its value will always stay between the range 0 and 1. Okay, now the famous example of probability is rolling a dice example. So when you roll a dice, you get 6 possible outcomes, right? You get 1, 2, 3, 4, and 5, 6 phases of a dice. Now each possibility only has one outcome. So what is the probability that on rolling a dice you'll get 3? The probability is 1 by 6, right? Because there's only one phase which has the number 3 on it. Out of 6 phases, there's only one phase which has the number 3. So the probability of getting 3 when you roll a dice is 1 by 6. Similarly, if you want to find the probability of getting a number 5, again the probability is going to be 1 by 6. All right. So all of this will sum up to 1. All right. So guys, this is exactly what probability is. It's a very simple concept. We all learned it in 8th standard onwards, right? Now let's understand the different terminologies that are related to probability. Now there are 3 terminologies that you often come across when we talk about probability. We have something known as random experiment. Okay, it's basically an experiment or a process for which the outcomes cannot be predicted with certainty. All right, that's why you use probability. You're going to use probability in order to predict the outcome with some sort of certainty. Sample space is the entire possible set of outcomes of a random experiment. An event is one or more outcomes of an experiment. So if you consider the example of rolling a dice, now let's say that you want to find out the probability of getting a 2 when you roll a dice. Okay, so finding this probability is the random experiment. The sample space is basically your entire possibility. Okay, so 1, 2, 3, 4, 5, 6 phases are there, and out of that you need to find the probability of getting a 2, right? So all the possible outcomes will basically represent your sample space. Okay, so 1 to 6 are all your possible outcomes. This represents your sample space. Now, event is one or more outcome of an experiment. So in this case, my event is to get a 2 when I roll a dice, right? So my event is the probability of getting a 2 when I roll a dice. So guys, this is basically what random experiment, sample space, and event really means. All right. Now, let's discuss the different types of events. There are two types of events that you should know about. There is disjoint and non-disjoint events. Disjoint events are events that do not have any common outcome. For example, if you draw a single card from a deck of cards, it cannot be a king and a queen, correct? It can either be king or it can be queen. Now, non-disjoint events are events that have common outcomes. For example, a student can get 100 marks in statistics and 100 marks in probability. All right. And also the outcome of a ball delivered can be a no ball and it can be a 6. Right. So this is what non-disjoint events are. All right. These are very simple to understand. Right. Now let's move on and look at the different types of probability distribution. All right. I'll be discussing the three main probability distribution functions. I'll be talking about probability density function, normal distribution, and central limit theorem. Okay. Probability density function, also known as PDF, is concerned with the relative likelihood for a continuous random variable to take on a given value. All right. So the PDF gives the probability of a variable that lies between the range A and B. So basically what you're trying to do is you're going to try and find the probability of a continuous random variable over a specified range. Okay, now this graph denotes the PDF of a continuous variable. Now this graph is also known as the bell curve, right? It's famously called the bell curve because of its shape. And there are three important properties that you need to know about a probability density function. Now the graph of a PDF will be continuous over a range. This is because you're finding the probability that a continuous variable lies between the ranges A and B, right? The second property is that the area bounded by the curve of a density function and the x-axis is equal to 1. Basically, the area below the curve is equal to 1, all right, because it denotes probability. Again, the probability cannot range more than 1. It has to be between 0 and 1. Property number 3 is that the probability that a random variable assumes a value between A and B is equal to the area under the PDF bounded by A and B. Okay, now what this means is that the probability value is denoted by the area of the graph. All right, so whatever value that you get here, which is basically 1, is the probability that a random variable will lie between the range A and B. All right, so I hope all of you have understood the probability density function. It's basically the probability of finding the value of a continuous random variable between the range A and B. All right. Now let's look at our next distribution, which is normal distribution. Now, normal distribution, which is also known as the Gaussian distribution, is a probability distribution that denotes the symmetric property of the mean, right? Meaning that the idea behind this function is that the data near the mean occurs more frequently than the data away from the mean. So what it means to say is that the data around the mean represents the entire data set. Okay, so if you just take a sample of data around the mean, it can represent the entire data set. Now, similar to the probability density function, the normal distribution appears as a bell curve. All right. Now, when it comes to normal distribution, there are two important factors. All right. We have the mean of the population and the standard deviation. Okay, so the mean in the graph determines the location of the center of the graph, right? And the standard deviation determines the height of the graph. Okay, so if the standard deviation is large, the curve is going to look something like this. All right, it'll be short and wide. And if the standard deviation is small, the curve is tall and narrow. All right, so this was it about normal distribution. Now let's look at the central limit theory. Now the central limit theory states that the sampling distribution of the mean of any independent random variable will be normal or nearly normal if the sample size is large enough. Now that's a little confusing. Okay, let me break it down for you. Now in simple terms, if we had a large population and we divided it into many samples, then the mean of all the samples from the population will be almost equal to the mean of the entire population. All right, meaning that each of the sample is normally distributed, right? So if you compare the mean of each of the sample, it will almost be equal to the mean of the population, right? So this graph basically shows a more clear understanding of the central limit theorem, right? You can see each sample here, and the mean of each sample is almost along the same line, right? Okay, so this is exactly what the central limit theorem states. Now, the accuracy or the resemblance to the normal distribution depends on two main factors, right? So the first is the number of sample points that you consider, all right? And the second is the shape of the underlying population. Now, the shape obviously depends on the standard deviation and the mean of a sample, correct? So guys, central limit theorem basically states that each sample will be normally distributed in such a way that the mean of each sample will coincide with the mean of the actual population. All right, in short terms, that's what central limit theorem states. All right, and this holds true only for a large data set. Mostly for a small data set, there are more deviations when compared to a large data set. It's because of the scaling factor, right? The smallest deviation in a small data set will change the value very drastically. But in a large data set, a small deviation will not matter at all. Now let's move on and look at our next topic, which is the different types of probability. Now this is an important topic because most of your problems can be solved by understanding which type of probability should I use to solve this problem, right? So we have three important types of probability. We have marginal, joint, and conditional probability. So let's discuss each of these. Now, the probability of an event occurring unconditioned on any other event is known as marginal probability or unconditional probability. So let's say that you want to find the probability that a card drawn is a heart. All right. So if you want to find the probability that a card drawn is a heart, the probability will be 13 by 52. Since there are 52 cards in a deck and there are 13 hearts in a deck of cards, right? And there are 52 cards in a total deck. So your marginal probability will be 13 by 52. That's about marginal probability. Now let's understand what is joint probability. Now, joint probability is a measure of two events happening at the same time. Okay, let's say that the two events are A and B. So the probability of event A and B occurring is the intersection of A and B. So for example, if you want to find the probability that a card is a 4 and a red, that would be joint probability. All right, because you're finding a card that is 4 and the card has to be red in color. So for the answer, this will be 2 by 52 because we have 1, 2 in hearts and we have 1, 2 in diamonds, correct? So both of these are red in color, therefore our probability is 2 by 52. And if you further down it, it is 1 by 26, right? So this is what joint probability is all about. Moving on, let's look at what exactly conditional probability is. So if the probability of an event or an outcome is based on the occurrence of a previous event or an outcome, then you called it as a conditional probability. Okay. So the conditional probability of an event B is the probability that the event will occur given that an event A has already occurred, right? So if A and B are dependent events, then the expression for conditional probability is given by this. Now, this first term on the left-hand side, which is P B of A, is basically the probability of event B occurring, given that event A has already occurred. All right. So like I said, if A and B are dependent events, then this is the expression. But if A and B are independent events, then the expression for conditional probability is like this, right? So guys, P of A and P of B is obviously the probability of A and probability of B, right? Now let's move on. Now, in order to understand conditional probability, joint probability, and marginal probability, let's look at a small use case. Okay. Now, basically, we're going to take a data set which examines the salary package and training undergone by candidates. Okay. Now, in this, there are 60 candidates without training and 45 candidates which have enrolled for Edureka's training. Right. Now, the task here is you have to assess the training with the salary package. Okay, let's look at this in a little more depth. So in total, we have 105 candidates, out of which 60 of them have not enrolled for Edureka's training and 45 of them have enrolled for Edureka's training. All right, this is a small survey that was conducted, and this is the rating of the package or the salary that they got. Right, so if you read through the data, you can understand. there were 5 candidates without Edureka training who got a very poor salary package. Okay, similarly, there are 30 candidates with Edureka training who got a good package, right? So guys, basically you're comparing the salary package of a person depending on whether or not they've enrolled for Edureka training, right? This is our data set. Now let's look at our problem statement. Find the probability that a candidate has undergone Edureka's training. Quite simple. Which type of probability is this? This is marginal probability, right? So the probability that a candidate has undergone Edureka's training is obviously 45 divided by 105. Since 45 is the number of candidates with Edureka training and 105 is the total number of candidates. So you get a value of approximately 0.42. All right, that's the probability of a candidate that has undergone Edureka's training. Next question. Find the probability that a candidate has attended Edureka's training and also has good package. Now this is obviously a joint probability problem, right? So how do you calculate this? Now since our table is quite formatted, we can directly find that people who have gotten a good package along with Edureka training are 30, right? So out of 105 people, 30 people have Edureka training and a good package, right? They're specifically asking for people with Edureka training. Remember that, right? The question is find the probability that a candidate has attended Edureka's training and also has a good package. All right, so you need to consider 2 factors. That is a candidate who's attended Edureka's training and who has a good package. So clearly that number is 30. 30 divided by total number of candidates, which is 105. Right? So here you get the answer clearly. Next, we have find the probability that a candidate has a good package given that he has not undergone training. Okay, now this is clearly conditional probability because here you're defining a condition. You're saying that you want to find the probability of a candidate who has a good package given that he's not undergone any training, right? The condition is that he's not undergone any training. All right. So the number of people who have not undergone training are 60, and out of that, 5 of them have got a good package, right? So that's why this is 5 by 60 and not 5 by 105, because here they've clearly mentioned has a good package given that he has not undergone training. So you have to only consider people who have not undergone training, right? So only 5 people who have not undergone training have gotten a good package, right? So 5 divided by 60, you get a probability of around 0.08, which is pretty low, right? Okay, so this was all about the different types of probability. Now let's move on and look at our last topic in probability, which is Bayes' theorem. Now guys, Bayes' theorem is a very important concept when it comes to statistics and probability. It is majorly used in naive Bayes algorithm. Those of you who aren't aware, naive Bayes is a supervised learning classification algorithm, and it is mainly used in Gmail spam filtering, right? A lot of you might have noticed that if you open up Gmail, you'll see that you have a folder called spam, right? All of that is carried out through machine learning, and the algorithm used there is naive Bayes, right? So now let's discuss what exactly the Bayes theorem is and what it denotes. The Bayes theorem is used to show the relation between one conditional probability and its inverse. All right. Basically, it's nothing but the probability of an event occurring based on prior knowledge of conditions that might be related to the same event. Okay, so mathematically, the Bayes theorem is represented like this, right? Like shown in this equation. The left-hand term is referred to as the likelihood ratio, which measures the probability of occurrence of event B given an event A. Okay. On the left-hand side is what is known as the posterior. Right, it is referred to as posterior, which means that the probability of occurrence of A given an event B. Right. The second term is referred to as the likelihood ratio. All right, this measures the probability of occurrence of B given an event A. Now, P of A is also known as the prior, which refers to the actual probability distribution of A, and P of B is again the probability of B. Right? This is the Bayes theorem. Now, in order to better understand the Bayes theorem, let's look at a small example. Let's say that we have 3 bowls. We have bowl A, bowl B, and bowl C. Okay, bowl A contains 2 blue balls and 4 red balls. Bowl B contains 8 blue balls and 4 red balls. Bowl C contains 1 blue ball and 3 red balls. Now, if we draw one ball from each bowl, what is the probability to draw a blue ball from a bowl A if we know that we drew exactly a total of 2 blue balls? Right? If you didn't understand the question, please reread it. I shall pause for a second or two. Right? So I hope all of you have understood the question. Okay, now what I'm going to do is I'm going to draw a blueprint for you and tell you how exactly to solve the problem. But I want you all to give me the solution to this problem, right? I'll draw a blueprint. I'll tell you what exactly the steps are, but I want you to come up with a solution on your own, right? The formula is also given to you. Everything is given to you. All you have to do is come up with a final answer, right? Let's look at how you can solve this problem. So first of all, what we'll do is let's consider A. All right, let A be the event of picking a blue ball from bag A. And let X be the event of picking exactly 2 blue balls, right? Because these are the 2 events that we need to calculate the probability of. Now, there are 2 probabilities that you need to consider here. One is the event of picking a blue ball from bag A. And the other is the event of picking exactly 2 blue balls. Okay, so these two are represented by A and X respectively. So what we want is the probability of occurrence of event A given X, which means that given that we're picking exactly 2 blue balls, what is the probability that we are picking a blue ball from bag A? So by the definition of conditional probability, this is exactly what our equation will look like, correct? This is basically occurrence of event A given an event X, and this is the probability of A and X, and this is the probability of X alone, correct? Now what we need to do is we need to find these 2 probabilities, which is probability of A and X occurring together and probability of X. Okay, this is the entire solution. So how do you find P, probability of X? This you can do in 3 ways. So first is white ball from A, either white from B or red from C. Now first is to find the probability of X. X basically represents the event of picking exactly 2 blue balls, right? So these are the 3 ways in which it is possible. So you'll pick 1 blue ball from bowl A and 1 from bowl B. In the second case, you can pick 1 from A and another blue ball from C. In the third case, you can pick a blue ball from bag B and a blue ball from bag C, right? These are the 3 ways in which it is possible. So you need to find the probability of each of this. Step 2 is that you need to find the probability of A and X occurring together. This is the sum of terms 1 and 2. Okay, this is because in both of these events, you're picking a ball from bag A, correct? So guys, find out this probability and let me know your answer in the comment section. All right, we'll see if you get the answer right. I gave you the entire solution to this. All you have to do is substitute the value, right? If you want a second or two, I'm going to pause on the screen so that you can go through this in a more clearer way, right? Remember that you need to calculate 2 probabilities. The first probability that you need to calculate is the event of picking a blue ball from bag A given that you're picking exactly 2 blue balls. Okay. The second probability you need to calculate is the event of picking exactly 2 blue balls. All right. These are the 2 probabilities you need to calculate. So remember that, and this is the solution. All right, so guys, make sure you mention your answers in the comment section. For now, let's move on and look at our next topic, which is the inferential statistics. So guys, we just completed the probability module, right? Now we'll discuss inferential statistics, which is the second type of statistics. We discussed descriptive statistics earlier, all right? So like I mentioned earlier, inferential statistics, also known as statistical inference, is a branch of statistics that deals with forming inferences and predictions about a population based on a sample of data taken from the population. All right. Now, the question you should ask is, how does one form inferences or predictions on a sample? The answer is you use point estimation. Okay. Now, you must be wondering, what is point estimation? Point estimation is concerned with the use of the sample data to measure a single value which serves as an approximate value or the best estimate of an unknown population parameter. That's a little confusing. Let me break it down to you. For example, in order to calculate the mean of a huge population, what we do is we first draw out the sample of the population and then we find the sample mean, right? The sample mean is then used to estimate the population mean. This is basically point estimate. You're estimating the value of one of the parameters of the population, right? Basically, the mean, you're trying to estimate the value of the mean. This is what point estimation is. There are two main terms in point estimation. There's something known as the estimator and there's something known as the estimate. Estimator is a function of the sample that is used to find out the estimate. All right. In this example, it's basically the sample mean, right? So a function that calculates the sample mean is known as the estimator, and the realized value of the estimator is the estimate, right? So I hope point estimation is clear. Now, how do you find the estimates? There are four common ways in which you can do this. The first one is method of moments. Here what you do is you form an equation in the sample data set and then you analyze a similar equation in the population data set as well, like the population mean, population variance, and so on. So in simple terms, what you're doing is you're taking down some known facts about the population and you're extending those ideas to the sample. All right. Once you do that, you can analyze the sample and estimate more essential or more complex values. Right. Next, we have maximum of likelihood. Now, this method basically uses a model to estimate a value. All right. Now, a maximum of likelihood is majorly based on probability. So there's a lot of probability involved in this method. Next, we have the Bayes estimator. This works by minimizing the errors or the average risk. Okay. The Bayes estimator has a lot to do with the Bayes theorem. All right. Let's not get into the depth of these estimation methods. Finally, we have the best unbiased estimators. In this method, there are several unbiased estimators that can be used to approximate a parameter. Okay. So guys, these were a couple of methods that are used to find the estimate. But the most well-known method to find the estimate is known as the interval estimation. Okay, this is one of the most important estimation methods. All right, this is where confidence interval also comes into the picture, right? Apart from interval estimation, we also have something known as margin of error. So I'll be discussing all of this in the upcoming slides. So first, let's understand what is interval estimate. Okay, an interval or range of values which are used to estimate a population parameter is known as an interval estimation. Right, that's very understandable. Basically, what they're trying to say is you're going to estimate the value of a parameter. Let's say you're trying to find the mean of a population. What you're going to do is you're going to build a range and your value will lie in that range or in that interval. All right, so this way your output is going to be more accurate because you've not predicted a point estimation. Instead, you have estimated an interval within which your value might occur, right? Okay, now this image clearly shows how point estimate and interval estimate are different. So guys, interval estimate is obviously more accurate because you're not just focusing on a particular value or a particular point in order to predict the probability. Instead, you're saying that the value might be within this range between the lower confidence limit and the upper confidence limit. All right, this just denotes the range or the interval. Okay, if you're still confused about interval estimation, let me give you a small example. If I stated that I will take 30 minutes to reach the theater, this is known as point estimation. Okay, but if I stated that I will take between 45 minutes to an hour to reach the theater, this is an example of interval estimation. All right, I hope it's clear now. Now, interval estimation gives rise to two important statistical terminologies. One is known as confidence interval and the other is known as margin of error. All right. So guys, it's important that you pay attention to both of these terminologies. Confidence interval is one of the most significant measures that are used to check how essential a machine learning model is. All right. So what is confidence interval? Confidence interval is the measure of your confidence that the interval estimated contains the population parameter or the population mean or any of those parameters, right? Now, statisticians use a confidence interval to describe the amount of uncertainty associated with the sample estimate of a population parameter. Now, guys, this is a lot of definition. Let me just make you understand confidence interval with a small example. Okay, let's say that you perform a survey and you survey a group of cat owners to see how many cans of cat food they purchase in 1 year. Okay. You test your statistics at the 99% confidence level and you get a confidence interval of 100, 200. This means that you think that the cat owners buy between 100 to 200 cans in a year. And also, since the confidence level is 99%, it shows that you're very confident that the results are correct. Okay. I hope all of you are clear with that. Right. So your confidence interval here will be 100 and 200, and your confidence level will be 99%. Right. That's the difference between confidence interval and confidence level. So within your confidence interval, your value is going to lie, and your confidence level will show how confident you are about your estimation. Right. I hope that was clear. Let's look at margin of error. Now, margin of error for a given level of confidence is the greatest possible distance between the point estimate and the value of the parameter that it is estimating. You can say that it is a deviation from the actual point estimate. Right? Now, the margin of error can be calculated using this formula. Now, ZC here denotes the critical value or the confidence interval, and this is multiplied by standard deviation divided by root of the sample size. All right, n is basically the sample size. Now let's understand how you can estimate the confidence intervals. So guys, the level of confidence, which is denoted by C, is the probability that the interval estimate contains a population parameter. Let's say that you're trying to estimate the mean. All right, so the level of confidence is the probability that the interval estimate contains the population parameter. So this interval between minus ZC and ZC, or the area beneath this curve, is nothing but the probability that the interval estimate contains a population parameter. Alright, it should basically contain the value that you are predicting. Right? Now these are known as critical values. This is basically your lower limit and your higher limit confidence level. Also, there's something known as the z-score. Now this score can be calculated by using the standard normal table. Alright, if you look it up anywhere on Google, you'll find the z-score table or the standard normal table. Okay, to understand how this is done, let's look at a small example. Okay, let's say that the level of confidence is 90%. This means that you are 90% confident that the interval contains the population mean. Okay, so the remaining 10%, which is out of 100%, the remaining 10% is equally distributed on these tail regions. Okay, so you have 0.05 here and 0.05 over here. Right? So on either side of C, you'll distribute the other leftover percentage. Now these z-scores are calculated from the table as I mentioned before. All right, 1.645 is calculated from the standard normal table. Okay, so guys, this is how you estimate the level of confidence. So to sum it up, let me tell you the steps that are involved in constructing a confidence interval. First, you'll start by identifying a sample statistic. Okay, this is the statistic that you will use to estimate a population parameter. This can be anything like the mean of the sample. Next, you will select a confidence level. Now, the confidence level describes the uncertainty of a sampling method. Right? After that, you'll find something known as the margin of error. Right? We discussed margin of error earlier. So you find this based on the equation that I explained in the previous slide. Then you'll finally specify the confidence interval. All right. Now let's look at a problem statement to better understand this concept. A random sample of 32 textbook prices is taken from a local college bookstore. The mean of the sample is so and so, and the sample standard deviation is this. Use a 95% confident level and find the margin of error for the mean price of all textbooks in the bookstore. Okay. Now this is a very straightforward question. If you want, you can read the question again. All you have to do is you have to just substitute the values into the equation. All right. So guys, we know the formula for margin of error. You take the z-score from the table. After that, we have deviation, which is 23.44, right? And that's standard deviation. And n stands for the number of samples. Here the number of samples is 32, basically 32 textbooks. So approximately your margin of error is going to be around 8.12. This is a pretty simple question. All right, I hope all of you understood this. Now that you know the idea behind confidence interval, let's move ahead to one of the most important topics in statistical inference, which is hypothesis testing, right? So basically, statisticians use hypothesis testing to formally check whether the hypothesis is accepted or rejected. Okay. Hypothesis testing is an inferential statistical technique used to determine whether there is enough evidence in a data sample to infer that a certain condition holds true for an entire population. So, to understand the characteristics of a general population, we take a random sample and we analyze the properties of the sample, right? We test whether or not the identified conclusion represents the population accurately, and finally, we interpret their results. Now, whether or not to accept the hypothesis depends upon the percentage value that we get from the hypothesis. Okay, so to better understand this, let's look at a small example. Before that, there are a few steps that are followed in hypothesis testing. You begin by stating the null and the alternative hypothesis. All right, I'll tell you what exactly these terms are. And then you formulate an analysis plan. All right, after that, you analyze the sample data. And finally, you can interpret the results, right? Now, to understand the entire hypothesis testing, we'll look at a good example. Okay. Now, consider four boys: Nick, John, Bob, and Harry. These boys were caught bunking a class and they were asked to stay back at school and clean their classroom as a punishment. Right? So, what John did is he decided that four of them would take turns to clean their classrooms. He came up with a plan of writing each of their names on chits and putting them in a bowl. Now, every day they had to pick up a name from the bowl and that person had to clean the class. Right? That sounds pretty fair enough. Now, it has been 3 days and everybody's name has come up except John's. Assuming that this event is completely random and free of bias, what is the probability of John not cheating? Right? What is the probability that he's not actually cheating? This can be solved by using hypothesis testing. Okay. So we'll begin by calculating the probability of John not being picked for a day. Right? So we're going to assume that the event is free of bias. So we need to find out the probability of John not cheating, right? First, we'll find the probability that John is not picked for a day, right? We get 3 out of 4, which is basically 75%. Now, 75% is fairly high. So if John is not picked for 3 days in a row, the probability will drop down to approximately 42%. Okay, so 3 days in a row meaning that is the probability drops down to 42%. Now let's consider a situation where John is not picked for 12 days in a row. The probability drops down to 3.2%. Okay, thus the probability of John cheating becomes fairly high, right? So in order for statisticians to come to a conclusion, they define what is known as the threshold value, right? Considering the above situation, if the threshold value is set to 5%, it would indicate that if the probability lies below 5%, then John is cheating his way out of detention. But if the probability is above the threshold value, then John is just lucky and his name isn't getting picked. So the probability and hypothesis testing give rise to two important components of hypothesis testing, which is null hypothesis and alternate hypothesis. Null hypothesis is basically approving the assumption. Alternate hypothesis is when your result disapproves the assumption. Right? Therefore, in our example, if the probability of an event occurring is less than 5%, which it is, then the event is biased. Hence, it proves the alternate hypothesis. So guys, with this, we come to the end of this session.
Let's go ahead and understand what exactly is supervised learning. So supervised learning is where you have the input variable X and the output variable Y, and you use an algorithm to learn the mapping function from the input to the output, as I mentioned earlier with the example of face detection. So it is called supervised learning because the process of an algorithm learning from the training dataset can be thought of as a teacher supervising the learning process. So if we have a look at the supervised learning steps, or what we'd rather say the workflow, so the model is used. As you can see here, we have the historic data, then we have the random sampling. We split the data into training dataset and the testing dataset. Using the training dataset, with the help of machine learning, which is supervised machine learning, we create statistical model. And then after we have a model which is being generated with the help of the training dataset, what we do is use the testing dataset for prediction and testing. What we do is get the output, and finally we have the model validation outcome. That was the training and testing. So if we have a look at the prediction part of any particular supervised learning algorithm, so the model is used for predicting outcome of a new data set. So whenever performance of the model degraded, the model is retrained, or if there are any performance issues, the model is retrained with the help of the new data. Now, when we talk about supervised learning, there are not just one, but quite a few algorithms here. So we have linear regression, logistic regression, decision tree, we have random forest, we have naive Bayes classifiers. So linear regression is used to estimate real values, for example, the cost of houses, the number of calls, the total sales, based on the continuous variables. So that is what linear regression is. Now, when we talk about logistic regression, it is used to estimate discrete values, for example, which are binary values like 0 and 1, yes or no, true and false, based on the given set of independent variables. So, for example, when we are talking about something like the chances of winning, or if we talk about winning, which can be the true or false, if will it rain today, it can be the yes or no. So it cannot be like when the output of a particular algorithm or the particular question is either yes, no, or a binary, then only we use a logistic regression. Now, next we have decision trees. So now these are used for classification problems. It works for both categorical and continuous dependent variables. And if we talk about random forest, so random forest is an ensemble of a decision tree. It gives better prediction and accuracy than decision tree. So that is another type of supervised learning algorithm. And finally, we have the naive Bayes classifier. So it is a classification technique based on the Bayes theorem with an assumption of independence between predictors.
A linear regression is one of the easiest algorithms in machine learning. It is a statistical model that attempts to show the relationship between two variables with a linear equation. But before we drill down to linear regression algorithm in depth, I'll give you a quick overview of today's agenda. So we'll start our session with a quick overview of what is regression, as linear regression is one of a type of regression algorithm. Once we learn about regression, its use case, the various types of it, next we'll learn about the algorithm from scratch, where I'll teach you its mathematical implementation first, then we'll drill down to the coding part and implement linear regression using Python. In today's session, we'll deal with linear regression algorithm using least square method, check its goodness of fit or how close the data is to the fitted regression line using the R-square method. And then finally, what we'll do, we'll optimize it using the gradient descent method. In the last part, on the coding session, I'll teach you to implement linear regression using Python. And the coding session would be divided into two parts. The first part would consist of linear regression using Python from scratch, where you will use the mathematical algorithm that you have learned in this session. And in the next part of the coding session, we'll be using scikit-learn for direct implementation of linear regression. So let's begin our session with what is regression? Well, regression analysis is a form of predictive modeling technique which investigates the relationship between a dependent and independent variable. A regression analysis involves graphing a line over a set of data points that most closely fits the overall shape of the data. A regression shows the changes in a dependent variable on the y-axis to the changes in the explanatory variable on the x-axis. Fine. Now you'd ask, what are the uses of regression? Well, there are major three uses of regression analysis. The first being determining the strength of predicators. The regression might be used to identify the strength of the effect that the independent variables have on the dependent variable. For example, you can ask a question like, what is the strength of relationship between sales and marketing spending? Or what is the relationship between age and income? Second is forecasting an effect. In this, the regression can be used to forecast effects or impact of changes. That is, the regression analysis help us to understand how much the dependent variable changes with the change in one or more independent variable. Fine. For example, you can ask question like, how much additional sale income will I get for each $1,000 spent on marketing? Third is trend forecasting. In this, the regression analysis predict trends and future values. The regression analysis can be used to get point estimates. In this, you can ask questions like what will be the price of Bitcoin in next 6 months, right? So next topic is linear versus logistic regression. By now, I hope that you know what a regression is. So let's move on and understand its type. So there are various kinds of regression like linear regression, logistic regression, polynomial regression, and others. All right. But for this session, we'll be focusing on linear and logistic regression. So let's move on and let me tell you what is linear regression and what is logistic regression. Then what we'll do, we'll compare both of them. All right. So starting with linear regression. In simple linear regression, we are interested in things like y equal mx plus c. So what we are trying to find is the correlation between x and y variable. This means that every value of x has a corresponding value of y in it if it is continuous. Alright? However, in logistic regression, we are not fitting our data to a straight line like linear regression. Instead, what we are doing, we are mapping y versus x to a sigmoid function. In logistic regression, what we find out is y 1 or 0 for this particular value of x. So thus we are essentially deciding true or false value for a given value of x. Fine. So as a core concept of linear regression, you can say that the data is modeled using a straight line, where in the case of logistic regression, the data is modeled using a sigmoid function. The linear regression is used with continuous variables. On the other hand, the logistic regression, it is used with categorical variable. The output or the prediction of a linear regression is the value of the variable. On the other hand, the output or prediction of a logistic regression is the probability of occurrence of the event. Now, how will you check the accuracy and goodness of fit? In case of linear regression, you have various methods like measured by loss, R squared, adjusted R squared, etc. While in the case of logistic regression, you have accuracy, precision, recall, F1 score, which is nothing but the harmonic mean of precision and recall. Next is ROC curve for determining the probability threshold for classification or the confusion matrix, etc. There are many. All right. So summarizing the difference between linear and logistic regression, you can say that the type of function you are mapping to is the main point of difference between linear and logistic regression. A linear regression maps a continuous x to a continuous y. On the other hand, a logistic regression maps a continuous x to the binary y. So we can use logistic regression to make category or true-false decisions from the data. Fine, so let's move on ahead. Next is linear regression selection criteria, or you can say when will you use linear regression. So the first is classification and regression capabilities. Regression models predict a continuous variable, such as the sales made on a day, or predict the temperature of a city. Their reliance on a polynomial like a straight line to fit a data set poses a real challenge when it comes towards building a classification capability. Let's imagine that you fit a line with the training points that you have. Now imagine you add some more data points to it. But in order to fit it, what do you have to do? You have to change your existing model. That is, maybe you have to change the threshold itself. So this will happen with each new data point you add to the model. Hence, the linear regression is not good for classification models. Fine. Next is data quality. Each missing value removes one data point that could optimize the regression. In simple linear regression, the outliers can significantly disrupt the outcome. Just for now, you can know that if you remove the outliers, your model will become very good. All right. So this is about data quality. Next is computational complexity. A linear regression is often not computationally expensive as compared to the decision tree or the clustering algorithm. The order of complexity for n training example and x features usually falls in either big O of x square or big O of xn. Next is comprehensible and transparent. The linear regression are easily comprehensible and transparent in nature. They can be represented by a simpler mathematical notation to anyone and can be understood very easily. So these are some of the criteria based on which you'll select the linear regression algorithm. Alright, next is where is linear regression used? First is evaluating trends and sales estimate. Well, linear regression can be used in business to evaluate trends and make estimates or forecasts. For example, if a company's sales have increased steadily every month for past few years, then conducting a linear analysis on the sales data with monthly sales on the y-axis and time on the x-axis. This will give you a line that predicts the upward trends in the sale. After creating the trend line, the company could use the slope of the lines to forecast sale in future months. Next is analyzing the impact of price changes. Well, linear regression can be used to analyze the effect of pricing on consumer behavior. For instance, if a company changes the price on a certain product several times, then it can record the quantity itself for each price level and then perform a linear regression with sold quantity as a dependent variable and price as the independent variable. This would result in a line that depicts the extent to which the customer reduced their consumption of the product as the price is increasing. So this result would help us in future pricing decisions. Next is assessment of risk in financial services and insurance domain. Well, linear regression can be used to analyze the risk. For example, a health insurance company might conduct a linear regression algorithm. How it can do? It can do it by plotting the number of claims per customer against its age. And they might discover that the older customers tend to make more health insurance claim. Well, the result of such analysis might guide important business decisions. Alright? So by now you have just a rough idea of what linear regression algorithm is, like what it does, where it is used, when you should use it. Alright, now let's move on and understand the algorithm in depth. So suppose you have independent variable on the x-axis and dependent variable on the y-axis. Alright, suppose this is the data point on the x-axis. The independent variable is increasing on the x-axis, and so does the dependent variable on the y-axis. So what kind of linear regression line you would get? You'd get a positive linear regression line. Alright, as the slope would be positive. Next is, suppose you have an independent variable on the x-axis which is increasing, and on the other hand, the dependent variable on the y-axis that is decreasing. So what kind of line will you get in that case? You'll get a negative regression line in this case, as the slope of the line is negative. And this particular line, that is line of y equal mx plus c, is a line of linear regression, which shows the relationship between independent variable and dependent variable. And this line is only known as line of linear regression. Okay. So let's add some data points to our graph. So these are some observation or data points on our graphs. Let's plot some more. Okay. Now all our data points are plotted. Now our task is to create a regression line or the best fit line. All right. Now, once our regression line is drawn, now it's the task of prediction. Now, suppose this is our estimated value or the predicted value, and this is our actual value. Okay. So what we have to do, our main goal is to reduce this error, that is to reduce the distance between the estimated or the predicted value and the actual value. The best fit line would be the one which had the least error or the least difference in estimated value and the actual value. All right. In other words, we have to minimize the error. This was a brief understanding of linear regression algorithm. Soon we'll jump to its mathematical implementation. But for then, let me tell you this. Suppose you draw a graph with speed on the x-axis and distance covered on the y-axis, with the time remaining constant. If you plot a graph between the speed traveled by the vehicle and the distance traveled in a fixed unit of time, then you will get a positive relationship. Alright? So suppose the equation of line is y equal mx plus c. Then in this case, y is the distance traveled in a fixed duration of time. X is the speed of vehicle, m is the positive slope of the line, and c is the y-intercept of the line. Alright? Suppose the distance remaining constant, you have to plot a graph between the speed of the vehicle and the time taken to travel a fixed distance. Then in that case, you'll get a line with a negative relationship. Alright? The slope of the line is negative. Here the equation of line changes to y equal minus of mx plus c, where y is the time taken to travel a fixed distance, x is the speed of vehicle, m is the negative slope of the line, and c is the y-intercept of the line. Alright? Now let's get back to our independent and dependent variable. So in that term, y is our dependent variable and x, that is our independent variable. Now let's move on and see the mathematical implementation of the things. Alright? So we have x equal 1, 2, 3, 4, 5. Let's plot them on the x-axis. So 0, 1, 2, 3, 4, 5, 6. Alright. And we have y as 3, 4, 2, 4, 5. Alright. So let's plot 1, 2, 3, 4, 5 on the y-axis. Now let's plot our coordinates one by one. So x equal 1 and y equal 3. So we have here x equal 1 and y equal 3. So this is our point 1, 3. So similarly, we have 1, 3, 2, 4, 3, 2, 4, 4, and 5, 5. Alright. So moving on ahead, let's calculate the mean of x and y and plot it on the graph. Alright. So mean of x is 1 plus 2 plus 3 plus 4 plus 5 divided by 5, that is 3. Alright. Similarly, mean of y is 3 plus 4 plus 2 plus 4 plus 5, that is 18. So 18 divided by 5, that is nothing but 3.6. Alright. So next what we'll do, we'll plot our mean, that is 3, 3.6 on the graph. Okay. So there's a point 3, 3.6. See, our goal is to find or predict the best fit line using the least square method. Alright. So in order to find that, we first need to find the equation of line. So let's find the equation of our regression line. Alright. So let's suppose this is our regression line, y equal mx plus c. Now we have an equation of line. So all we need to do is find the value of m and c, where m equals summation of x minus x bar multiplied by y minus y bar upon the summation of x minus x bar whole square. Don't get confused. Let me resolve it for you. Alright. So moving on ahead, as a part of formula, what we are going to do, we'll calculate x minus x bar. So we have x as 1 minus x bar as 3. So 1 minus 3, that is minus 2. Next we have x equal 2 minus its mean 3, that is minus 1. Similarly, we have 3 minus 3 is 0, 4 minus 3 1, 5 minus 3 2. Alright. So x minus x bar, it's nothing but the distance of all the point through the line y equal 3. And what does this y minus y bar implies? It implies the distance of all the point from the line x equal 3.6. Fine. So let's calculate the value of y minus y bar. So starting with y equal 3 minus value of y bar, that is 3.6. So it is 3 minus 3.6. How much? Minus of 0.6. Next is 4 minus 3.6. That is 0.4. Next 2 minus 3.6. That is minus of 1.6. Next is 4 minus 3.6. That is 0.4. Again 5 minus 3.6. That is 1.4. Alright. So now we are done with y minus y bar. Fine. Now next we'll calculate x minus x bar whole square. So let's calculate x minus x bar whole square. So it is minus 2 whole square, that is 4, minus 1 whole square, that is 1, 0 square 0, 1 square 1, 2 square 4. Fine. So now in our table we have x minus x bar, y minus y bar, and x minus x bar whole square. Now what we need the product of x minus x bar multiplied by y minus y bar. Alright. So let's see the product of x minus x bar multiplied by y minus y bar. That is minus of 2 multiplied by minus of 0.6, that is 1.2. Minus of 1 multiplied by 0.4, that is minus of 0.4. 0 multiplied by minus of 1.6, that is 0. 1 multiplied by 0.4, that is 0.4. And next 2 multiplied by 1.4, that is 2.8. Alright. Now almost all the parts of our formula is done. So now what we need to do is get the summation of last two columns. Alright. So the summation of x minus x bar whole square is 10, and the summation of x minus x bar multiplied by y minus y bar is 4. So the value of m will be equal to 4 by 10. Fine. So let's put this value of m equals 0.4 in our line y equal mx plus c. So let's fill all the points into the equation and find the value of c. So we have y as 3.6. Remember the mean y? M as 0.4, which we calculated just now. X as the mean value of x, that is 3. And we have the equation as 3.6 equals 0.4 multiplied by 3 plus c. Alright. That is 3.6 equal 1.2 plus c. So what is the value of c? That is 3.6 minus 1.2. That is 2.4. Alright. So what we had m equals 0.4, c as 2.4. And then finally, when we calculate the equation of regression line, what we get is y equal 0.4 times of x plus 2.4. So this is the regression line. Alright. So this is how you're plotting your points. This is your actual point. Alright. Now for given m equals 0.4 and c equal 2.4, let's predict the value of y for x equal 1, 2, 3, 4 and 5. So when x equal 1, the predicted value of y will be 0.4 multiplied by 1 plus 2.4, that is 2.8. Similarly, when x equal 2, predicted value of y will be 0.4 multiplied by 2 plus 2.4, that equals to 3.2. Similarly, x equal 3, y will be 3.6. X equal 4, y will be 4.0. X equal 5, y will be 4.4. So let's plot them on the graph, and the line passing through all these predicting points and cutting y-axis at 2.4 is the line of regression. Now your task is to calculate the distance between the actual and the predicted value, and your job is to reduce the distance. Alright? Or in other words, you have to reduce the error between the actual and the predicted value. The line with the least error will be the line of linear regression or regression line, and it will also be the best fit line. All right. So this is how things work in computer. So what it performs n number of iteration for different values of m. For different values of m, it will calculate the equation of line where y equal mx plus c, right? So as the value of m changes, the line is changing. So iteration will start from 1, all right, and it will perform n number of iteration. So after every iteration, what it will do, it will calculate the predicted value according to the line and compare the distance of actual value to the predicted value. And the value of m for which the distance between the actual and the predicted value is minimum will be selected as the best fit line. All right. Now that we have calculated the best fit line, now it's time to check the goodness of fit or to check how good a model is performing. So in order to do that, we have a method called R-square method. So what is this R-square? Well, R-squared value is a statistical measure of how close the data are to the fitted regression line. In general, it is considered that a high R-squared value model is a good model. But you can also have a low R-squared value for a good model as well, or a high R-squared value for a model that does not fit at all. All right. It is also known as coefficient of determination or the coefficient of multiple determination. Let's move on and see how R-square is calculated. So these are our actual values plotted on the graph. We had calculated the predicted values of y as 2.8, 3.2, 3.6, 4.0, 4.4. Remember when we calculated the predicted values of y for the equation y predicted equals 0.4 times of x plus 2.4 for every x equal 1, 2, 3, 4, and 5. From there, we got the predicted values of y. All right. So let's plot it on the graph. So these are a point, and the line passing through these points are nothing but the regression line. All right. Now, what you need to do is you have to check and compare the distance of actual minus mean versus the distance of predicted minus mean. All right. So basically what you're doing, you're calculating the distance of actual value to the mean to distance of predicted value to the mean. All right. So there's nothing but R square. In mathematically, you can represent R square as summation of y predicted values minus y bar whole square divided by summation of y minus y bar whole square, where y is the actual value, yp is the predicted value, and y bar is the mean value of y. That is nothing but 3.6. So remember, this is our formula. So next what we'll do, we'll calculate y minus y bar. So we have y as 3, y bar as 3.6. So we'll calculate it as 3 minus 3.6, that is nothing but minus of 0.6. Similarly, for y equal 4 and y bar equal 3.6, we have y minus y bar as 0.4. Then 2 minus 3.6, it is 1.6. 4 minus 3.6, again 0.4. And 5 minus 3.6, it is 1.4. So we got the value of y minus y bar. Now, what we have to do, we have to take it square. So we have minus of 0.6 square as 0.36, 0.4 square as 0.16, minus of 1.6 square as 2.56, 0.4 square as 0.16, and 1.4 square as 1.96. Now as a part of formula, what we need our yp minus y bar value. So these are yp values and we have to subtract it from the mean of y. So 2.8 minus 3.6, that is minus 0.8. Similarly, we'll get 3.2 minus 3.6, that is 0.4. And 3.6 minus 3.6, that is 0. 4.0 minus 3.6, that is 0.4. Then 4.4 minus 3.6, that is 0.8. So we calculated the value of yp minus y bar. Now it's our turn to calculate the value of yp minus y bar whole square. Next we have minus of 0.8 square as 0.64. Minus of 0.4 square as 0.16, 0 square 0, 0.4 square as again 0.16, and 0.8 square as 0.64. Alright, now as a part of formula, what it suggests me to take the summation of yp minus y bar whole square and summation of y minus y bar whole square. Alright, let's see. So on summating y minus y bar whole square, what you get is 5.2. And summation of yp minus y bar whole square, you get 1.6. So the value of R square can be calculated as 1.6 upon 5.2. Fine. So the result which you'll get is approximately equal to 0.3. Well, this is not a good fit. Alright. So it suggests that the data points are far away from the regression line. Alright. So this is how your graph will look like when R square is 0.3. When you increase the value of R square to 0.7, so you'll see that the actual value would lie closer to the regression line. When it reaches to 0.9, it comes more close. And when the value approximately equals to 1, then the actual values lies on the regression line itself. For example, in this case, if you get a very low value of r square, suppose 0.02, so in that case, what you'll see that the actual values are very far away from the regression line. Or you can say that there are too many outliers in your data. You cannot forecast anything from the data, all right? So this was all about the calculation of r square. Now you might get a question like, are low values of r square always bad? Well, in some field, it is entirely expected that our r square value will be low. For example, any field that attempts to predict human behavior, such as psychology, typically has r squared values lower than around 50%, through which you can conclude that humans are simply harder to predict than the physical process. Furthermore, if your r squared value is low, but you have statistically significant predicators, then you can still draw important conclusion about how changes in the predicator values are associated with the changes in the response value. Regardless of the r squared, the significant coefficient still represent the mean change in the response for 1 unit of change in the predicator, while holding other predicators in the model constant. Obviously, this type of information can be extremely valuable. Alright? Alright, so this was all about the theoretical concept. Now let's move on to the coding part and understand the code in depth. So for implementing linear regression using Python, I'll be using Anaconda with Jupyter Notebook installed on it. So alright, this is our Jupyter Notebook and we are using Python 3.0 on it. Alright, so we are going to use a data set consisting of head size and human brain of different people. Alright, so let's import our data set. %matplotlib inline. We are importing NumPy as NP, Pandas as PD, and Matplotlib. And from Matplotlib, we are importing PyPlot of that as PLT. Alright. Next, we'll import our data headbrain.csv and store it in the data variable. Let's execute the run button and see the output. So this asterisk symbol, it symbolizes that it's still executing. So there's our output. Our data set consists of 237 rows and 4 columns. We have columns as gender, age range, head size in centimeter cube, and brain weights in gram. Fine. So this is our sample data set. This is how it looks. It consists of all these data set. So now that we have imported our data, so as you can see, there are 237 values in the training set. So we can find a linear relationship between the head size and the brain weights. So now what we'll do, we'll collect X and Y. The X would consist of the head size values and the Y would consist of brain weight values. So collecting X and Y, let's execute the run. Done. Next, what we'll do, we need to find the values of B1 or B0, or you can say M and C. So we'll need the mean of X and Y values. First of all, what we'll do, we'll calculate the mean of X and Y. So mean X equal np.meanX. So mean is a predefined function of NumPy. Similarly, mean underscore y equal np.mean of y. So what it will return? It will return the mean values of y. Next, we'll check the total number of values. So m equal length of x. Alright. Then we'll use the formula to calculate the values of b1 and b0 or m and c. Alright. Let's execute the run button and see what is the result. So as you can see here on the screen, we have got b1 as 0.263 and b0 as 325.57. Alright, so now that we have our coefficient, so comparing it with the equation y equal mx plus c, you can say that brain weight equals 0.263 multiplied by head size plus 325.57. So you can say that the value of m here is 0.263 and the value of c here is 325.57. Alright, so this is our linear model. Now let's plot it and see graphically. Let's execute it. So this is how our plot looks like. This model is not so bad, but we need to find out how good our model is. So in order to find it, there are many methods like root mean square method, the coefficient or determination, or the R square method. So in this tutorial, I have told you about R square method. So let's focus on that and see how good our model is. So let's calculate the R square value. Alright. Here SS underscore T is the total sum of square. SS underscore R is the total sum of square of residuals. And R square as per formula is 1 minus total sum of squares upon total sum of square of residuals. Alright. Next, when you execute it, you'll get the value of R square as 0.63, which is pretty very good. Now that you have implemented simple linear regression model using least square method, Let's move on and see how will you implement the model using machine learning library called scikit-learn. Alright. So this scikit-learn is a simple machine learning library in Python. Building machine learning model are very easy using scikit-learn. So suppose there's a Python code. So using the scikit-learn libraries, your code shortens to this length. Alright. So let's execute the run button and see. You'll get the same R2 score.
So today we'll be discussing logistic regression. So let's move forward and understand the what and why of logistic regression. Now this algorithm is most widely used when the dependent variable, or you can say the output, is in the binary format. So here you need to predict the outcome of a categorical dependent variable. So the outcome should be always discrete or categorical in nature. Now by discrete, I mean the value should be binary, or you can say you just have two values. It can either be 0 or 1. It can either be yes or a no, either be true or false, or high or low. So only these can be the outcomes. So the value which you need to predict should be discrete, or you can say categorical in nature. Whereas in linear regression, we have the value of y, or you can say the value you need to predict is in a range. So that is how there is a difference between linear regression and logistic regression. Now you must be having a question, why not linear regression? Now guys, in linear regression, the value of y, or the value which you need to predict, is in a range. But in our case, as in the logistic regression, we just have two values. It can be either 0 or it can be 1. It should not entertain the values which is below 0 or above 1. But in linear regression, we have the value of y in the range. So here, in order to implement logistic regression, we need to clip this part. So we don't need the value that is below 0, or we don't need the value which is above 1. So since the value of y will be between only 0 and 1, that is the main rule of logistic regression, the linear line has to be clipped at 0 and 1. Now once we clip this graph, it would look somewhat like this. So here you are getting a curve which is nothing but three different straight lines. So here we need to make a new way to solve this problem. So this has to be formulated into an equation, and hence we come up with logistic regression. So here the outcome is either 0 or 1, which is the main rule of logistic regression. So with this, our resulting curve cannot be formulated. So hence our main aim to bring the values to 0 and 1 is fulfilled. So that is how we came up with logistic regression. Now here, once it gets formulated into an equation, it looks somewhat like this. So guys, this is nothing but a S-curve, or you can say the sigmoid curve or sigmoid function curve. So this sigmoid function basically converts any value from minus infinity to infinity to your discrete values, which a logistic regression wants, or you can say the values which are in binary format, either 0 or 1. So if you see here, the values are either 0 or 1, and this is nothing but just a transition of it. But guys, there's a catch over here. So let's say I have a data point that is 0.8. Now how can you decide whether your value is 0 or 1? Now here you have the concept of threshold, which basically divides your line. So here threshold value basically indicates the probability of either winning or losing. So here by winning I mean the value is equals to 1, and by losing I mean the value is equals to 0. But how does it do that? Let's say I have a data point which is over here. Let's say my cursor is at 0.8. So here I'll check whether this value is less than my threshold value or not. Let's say if it is more than my threshold value, it should give me the result as 1. If it is less than that, then it should give me the result as 0. So here my threshold value is 0.5. Now I need to define that if my value, let's say 0.8, it is more than 0.5, then the value shall be rounded off to 1. And let's say if it is less than 0.5, let's say I have a value 0.2, then should reduce it to 0. So here you can use the concept of threshold value to find your output. So here it should be discrete, it should be either 0 or it should be 1. So I hope you caught this curve of logistic regression. So guys, this is the sigmoid S curve. So to make this curve, we need to make an equation. So let me address that part as well. So let's see how an equation is formed to imitate this functionality. So over here we have an equation of a straight line, which is y is equals to mx plus c. So in this case, I just have only one independent variable. But let's say if we have many independent variables, then the equation becomes m1x1 plus m2x2 plus m3x3 and so on till mn(xn). Now let us put in b and x. So here the equation becomes y is equals to b1x1 plus b2x2 plus b3x3 and so on till bn(xn).